Okay, I think I'm going to start. So just like to welcome everybody to this. This is the Lambda calculus tutorial. Hopefully you read the description of this, especially the part about nothing usefully practical being done in here. So if you're expecting something that you're going to be able to use at work, you're probably in the wrong place. Also, just a couple of little logistic things. You will get the most out of this by typing along and trying the code out as we go and experimenting. And I will also emphasize that almost nothing is obvious in here. So I want you to meet your neighbor at the table there and feel free to chat back and forth, what is he talking about, and what are you doing? You're gonna get more by trying stuff out, talking with each other. I also have an assistant, Brian Ward, in the back with a traveling microphone. So if you have a question or something, just to make it a little bit easier for you people to maybe raise your hand, and he'll come find you, and you can ask the question. Little background on the tutorial. We're going to be talking about the Python's Lambda function a lot. Okay, so you've probably seen things like this before, hopefully. One thing about Lambda is that it is a way of defining a function in Python. It's just another way of defining a function. And one kind of interesting challenge with Lambda is how to introduce it when teaching Python. I actually teach a lot of Python classes, and this is something that usually comes up at some point, maybe with the sort function or something, and it's oh, you use the Lambda function, and then you have to sort of describe this to people. I think that, we have Stuart here who's taught a lot of classes, and one question that sometimes comes out is why is it called Lambda? I don't know, does anybody encounter this in either just teaching Python to people or anything? It's kind of a weird name, right? It's Lambda. What's that about? And then you start answering that. It's well, it's called Lambda because everybody else calls it Lambda, which is sort of a non-answer, right? That's just deflecting to some, non-thing. And then people are going to ask, well, why does everybody else call it Lambda? And then it's well, they called it Lambda in Lisp or Scheme or something. Okay, so it comes from Lisp, and it's well, why did they call it Lambda? And it's well, they took it from the Lambda calculus. And then if somebody asks what's the Lambda calculus, then you start running away and horror, and actually just personally, before doing this tutorial, it's I didn't even really know the Lambda calculus at all. I think I'd crossed paths with it in graduate school at some point, but at the time that I did it, I was studying for qualifying exams and spending the other half of my time playing Duke Nukem or something like that. And my memory of the Lambda calculus was just zero. So this tutorial is kind of born out of that. It's what is Lambda calculus? And I don't know, how does it work? I think it's going to be really cool. My experience with it is this is just insane and crazy, and I think it'll be fun. So that's what we're going to talk about, and I'm going to kind of step you through it in sort of maybe an unusual way. But the thing that I wanted to start with is actually that thing that I got up on the slide, the Lambda X there. How would you teach what's happening there to a 10-year-old? I have a 10-year-old kid. He's taking, he's in 3rd, 4th grade. They're doing math. If you want to, forget the Lambda part of that for a second, but just if you were to describe just how a function works, what's going on there? How would you teach that? Yeah.
So if you think about school, right? We all kind of learn functions at some point, right? They map a set of numbers to another set of numbers, right?
Yeah.
And kind of along with those, right? If you have the 3x plus 1, that's a function that you'll see in math class. But the Lambda is particularly unnamed function.
Yeah.
Right? In school, functions almost never have names unless it's a sign.
Yeah. But it's not even about the name. If you're just if you have a 10-year-old and you're just saying f of 4, what do you do there? You just it may be overthinking. It's you just replace the x. If you were to describe what that does, it's you replace the x with 4. And then you do math, like it's like 3 times 4 plus 1. And you sort of describe the function as like, well, the whole thing that's just going on there is you just replace the x. Function, substitute the x. There's some interesting things that you could get into with like a kid, like if you said like, well, what if you have f2 plus 3? Like, how does that work? There's their issue. It's like, okay, well, you're going to get 16, but like, do you do the 2 plus 3 first? Like, do you get 3 times 5 plus 1? Is that how you do that? Or do you have, do you do that? Like, do you just literally take like the 2 plus 3 and like plug it in for the x? I mean, there are some variations there, but basically function, you take the thing in parentheses and you substitute the x. Okay, so you have that. Now, the thing that we're gonna start with is what if you were teaching programming and you decided right at this point to stop, saying you don't need to know anything else. Okay, so what if you had this sort of thought experiment where it's like you actually do not need anything else other than substituting the x. So imagine that you had Python. Okay, so you're going to do like the scene from like the Holy Grail on Python, and you're going to like start chopping things away from Python, like non-essential parts of Python. I'll help you out here, like no packages or modules. That would solve a lot of problems, right? You get rid of that. What if you had like no objects? Or no numbers? Or no strings? Or no data types? You just basically just like start carving it away. Or you just start stripping things down, and it's like how much of it could you actually cut away and still actually have something that you could compute with? Like do anything useful. And the thing that we're gonna talk about here is actually an idea, which is what if functions are actually the only thing in the universe, and not only functions but just single argument functions, and nothing else exists. So you can write a function like you can say f of x, and you can have that, but you're not allowed to do anything else in your whole language. Now this is going to get a little bit mind-bending because you're thinking of function like if you said return x plus 1, no. There's no numbers, okay? So, and there's no plus either. We don't have any operator, okay? So that's a little weird. You can't do this because we only have single argument function. This actually solves a lot of problems, by the way, because if you only have one argument, you don't need defaults or keywords or positional only arguments or anything. Like if you're following that debate, it sort of collapses down. So you can have multiple arguments. You could do something like that, but it's hard to decide whether that's very useful. It's sort of under-specified, right? I mean, you could have a function x, takes an x and returns x. They always take an argument. So 0 argument functions are not allowed. Yeah.
Usually ifs are not allowed.
There's no if statements. There's no, we got rid of control flow. I didn't put it on the list, but control flow. I mean, once you start thinking about control flow, it's going to lead to things like exceptions and all that's evil, and no, we don't want, no. So yeah, control flow is gone. The only thing that you have is basically single argument function. You could do things like this. That's okay. X is a function. The reason it's a function is because functions are the only thing that exists in the whole universe. So by default, it has to be a function. Not clear what that does. You could also create a function. I mean, this is technically allowed. I mean, you could do something like that. It's a little strange, but I mean, you could have a function that defines a new single argument function only. Okay, it has to be single argument. The only thing that you can do with a function is call a function. Keep in mind, we have no numbers or operators or anything other than just calling a function, and you could return that. So you can do this sort of stuff, but now that the challenge is, could you actually do anything with that? Okay, I mean, again, kind of mad, you've taken Python, you've just chopped everything off of it except for functions, single argument functions. Is there any like thing in the real world of any kind, anything that you can do with this like programming restriction? So I'm going to let you ponder that for a couple of minutes here. It's a little tough, I think. Well, and, I'm trying to gauge whether anybody has any thoughts on zero thought. Yeah, it's the thing that's a little weird about it is it feels like extremely abstract at this point. Like, keep in mind, like, did we just lose audio for a second? Do you have audio back there? I think we lost audio. Do you have audio? You're getting audio in the recording? Okay, maybe it's just the speaker. Okay. No, the thing. It's like at this point, it actually feels like very, very weirdly abstract. I mean, just to emphasize, in this system, there is literally nothing other than a single argument function. There are no bits or anything. Yeah. As long as you can return a single argument function. Actually, that's an interesting, like multiple things, like that would imply the existence of a data structure or something like a tuple. So as long as your multiple things is a single argument function. Functions can be passed around, yes. So you can pass functions, you can turn functions, as long as they're single argument functions.
The feeling is that you could end up with something magnificent and Turing complete if only you could pass one thing in at the very beginning. Then you could have.
Well, as long as it's a function,
Yeah,
right? Yeah. No, it's a real brain. Maybe one way to think about this is it's like a weird escape room that I've put you in from coding. It's like, okay, we got this style guide, which is extremely easy to remember because single argument functions. That's it. But the question is like, how do you do anything with it? So.
You have a namespace.
Actually, names are not technically allowed either, but I'm going to break that rule just to be able to do anything. No. It turns out that having names of like global variables is not really technically allowed either, but we're gonna lighten that rule. So, all right. So in looking at this, okay. So at first glance, it's going to be like this is just okay. I don't even know where to start with this, and so. So I thought I would start you with actually something real that you could model with this. It's going to be something really unexpected, I think, but you could model a switch using this. I was trying to think about how to make the tutorial go full stack down to the bare metal. Basically, you got to talk about electricity and other things. So let's say you have like a switch like that. Okay, so this is a switch like left right. It has two inputs A and B. It has an output on that. That is actually something that you could model in this system. But the way it's going to work is going to be a little strange. Okay. I'm going to write a function left that takes in a single argument because everything has to take single argument. And then inside, whoa, okay, a little audio excitement there. I'm going to define a function f that returns the A, and then I return the function back. Now, at first glance, that's going to look really weird. I'm going to write a function right that does the same thing. Well, almost the same thing. Okay, so I'm going to have you type that in. Now, how this is going to work is this is essentially like a chaining of functions where you provide like an argument to the first, like the outer function. You say like, okay, left, A, that's 5 volts or something. Okay, think electricity. And then what it is doing is returning a function back. Like it's returning this f back.
But you have a string in there.
Well, okay, yeah, well, ignore that for the moment. No, ignore that, no. Yeah, I'm breaking the rules a little bit, but you're onto something important here in a second. Okay, so what's happening is like two inputs are coming in. There's like an A, which is like the 5 volts, and then the B is like maybe ground or something. And what left is doing is it picks out the A, basically. Like if you're in the left position, it means that you're picking the A. You're connected to the A. And if you were to do the same thing with like the right function, it would come back and it would say, well, you're connected to the ground. Now, the thing that's kind of wild about this is that these functions, they don't really represent like a thing. It's not a bit. It's not a piece of data or anything. What they're representing is a behavior, basically. Like the behavior of left means that you're connected to the A. And the behavior of the right means you're connected to the B. In some sense, it doesn't really care what you pass in here. Like, I mean, like you could have left of loud, like maybe like loud soft or something. If you're in the left, it means you're loud. If you're right, it means you're soft. It's still a little abstract, but essentially you're modeling, again, like a behavior. It's like the behavior of a switch is that if it's in the left position, you're connected to the A input. And if you're in the right position, you're connected to the B input. And that is what is happening here. Let me just pause for a second. Again, I definitely want you to try typing in the code as we go and trying this stuff out. So I'll give you a minute to try that. I do, while you're doing that, by the way, I do want to make a mention that this technique that we're doing here, okay, this is not part of our system, but this technique of writing single argument functions, like let's say you had a function add, like that, where it took 2 arguments. You could rewrite that in a really funny way. Using single arguments. This is not going to win you points at work doing some trick like that, but you can take like multiple argument functions and turn them into single argument functions. This is something known as currying. If you've ever heard that term before, it's sometimes something people will throw around that term. It's basically a way of you can take like multiple argument functions and just kind of turn them into single argument functions. Again, you're going to have a lot of explaining to do at a code review if you were to show up with something like that normally, but that's what's happening there. All right, how are people doing? Questions? Okay, next thing we're going to talk about is, could you take that and spin it into the notion of truth? Most computers do have a notion of Boolean values, right? Like you have true and false. Could you represent like true and false using this scheme in some way? And the reason that I kind of did the switch example is that you could think about it like that. Like think about your computer. What is a true value on your computer? It's an electrical device, right? I mean, it's electricity flowing around in there. What is true? Yeah, something. I mean, it's like a bit on your computer. What is a bit? I mean, is it like, it's probably like, it's either like 5 volts or 3 volts or something. I mean, it's like there's electricity on it or it's the ground. It's one or the other. And it turns out that maybe that switch code that we had is the same thing that we could kind of do for true and false. I'm gonna switch over to Lambda there just to shorten the syntax a little bit, shorten the amount of typing. So maybe true and false are kind of the same thing. Basically, what true is it's like a behavior. Basically, true means that you're connected to the first value, whatever it is, 5 volts or something. If we're talking about computers again, and false is the opposite. It's kind of arbitrary in a way. I mean, but if you think about like true and false values, it's like you have true and you have false, and true is supposed to be the opposite of false. I'm never quite sure with the news these days, but you know, but like normally, like true and false are meant to be opposites, and that's kind of what's going on here. You've got X and Y, true and false. Like true is one of them, and false is the other one, and again, it's a little odd because we're not representing true and false as a concrete thing. It's not a bit. It's not a piece of data. Anything. It's strictly like a behavior. The behavior of true is that you're connected to the first thing, and the behavior of false is that you're connected to the second thing. Question up here. So.
I'm a little bothered by the absence of fact-finding.
Fact-finding?
Yeah, you know, it seems like we're, it's like the thing where, you ask the reporter, are you sure there's cannibalism going on? He says, no, we're just reporting that there's cannibalism going on.
Right.
And so we have true as the left value, I mean, because it's still just a switch, and false is the right value. So the hair that stands up on my neck is that we won't, in some sense, be able to have the sort of fact-finding that you need to have an actual Boolean structure.
Yeah, there's like nothing concrete to really hang on to here. It's like true. I find this like really disturbing. It's like true is not a thing. It's just like, well, it's whatever it's whatever the X is. It's like that's what true is. But we haven't. But the only thing that we know about the rules here is that technically it has to be a single argument function. These values like 5 volts and ground, that's bogus. They normally can't do that. So, I mean, like normally I would have to do something like this. I'd have to say, well, you can do true and false or something. Like that would be okay. Or you could have a function of one argument. Like you could say lambda f, x is x. I mean, I could say true of f, false, or like. But that is like making my head explode because it's like it feels like even more ungrounded than it was before, right? Doing that. So it's very weird. It gets even weirder if I challenge you to start implementing the Boolean operators like not, or, and or. Let me take that away. No. Here's a challenge. Like, how could you define not? And just to be clear about the behavior of not true is basically false, and not false is basically true. At least it was the last time I checked, anyway. So, yeah, Brian, you want to try to get people to do the mic on the question here? Yeah.
So just to sort of keep inventory here, are you cheating again here for narrative purposes at the end, or do we have a universe that has identity?
I'm cheating with Python here.
Okay.
No, the assert statement is that's some Python stuff. Yeah. It becomes a little bit hard to talk about if there's literally nothing, but it's. So the question is, how in the world would you do not? And this is where things are going to, I mean, it's already probably very abstract and weird. I mean, it's like true and false are functions, and like, and what does it mean? And so like, let's think about the not for a second. The only thing that exists in this universe is functions. So one thing that we can say about not is that x is definitely a function. Okay, we know it's a function because that's the only thing that exists. So that we have 100% guarantee that it's a function. Okay, so we know that it's going to be a function. The other thing that we know is that if our intent is to pass true and false to that thing, those are functions that have the two arguments. Remember, the behavior of true is that you choose the first thing, and the behavior of false is you choose the second thing. So we know that we can do this. Like we say return x something and then something else. And exactly right. So comment up here, just reverse it. So if x is true, what you want to do is pick out false. Like the behavior of true is you pick the first thing. And if it's false, you pick out the second thing. So not true is false. And not false is true. Okay, so looks a little strange. Leave that up there. Gets a bit more interesting if you start thinking about and or function. What if you wanted to have something like that? I'm gonna let you ponder this one for a second. I'm gonna give you a little hint on this one. One hint here is to understand how Python does and ors. So if I were to say 2 and 3 in Python, keep in mind this is not loud in our system because we have no numbers, but we're just talking about Python here. What does that return? So that returns 3. But what about 0 and 3? What if I were to do 0 and 3? What does that return? You're kind of seeing like a hint of how to do this from Python. Basically, if the first item in AND is a true value, Python goes to the second value and uses that to determine the result. Like if the first thing is true, the only way you know whether it's like true or false is to look at the second value. If the first thing is false, like 0, then you're just done. You know that it's false. So like what comes back is 0. That is going to be a little bit of the trick here. We're going to look at the first value, the x. We're going to basically look at it and say, okay, what are you, x? Are you a true value or are you a false value? And then I'm going to return some things back. Just give her a few seconds to kind of ponder it here. What do you think you would what would go in this first parenthesis here?
True. Yeah.
No, the x. Why? What would be x of x?
Somebody said I think you put y in there basically. Like if x is true, the behavior of true is you pick the first thing, right? It's like true picks the first thing. So if it's true, the result of and is solely determined by what y is, right? I mean, like if x is true, then, well, whatever y is, that is the result. Like if y is true, then it's true. If y is false, then it's false. If x is false, then what is the result? It could just be x. Like if x is false, then the thing is false, and you could do that. No, it turns out that exactly does that. It's a little, it's kind of mind-boggling, but you can try it out. Like and true is true. And true and false is false. And false and true is false, and false and false is false. So it is giving you the Boolean logic doing that. But it's a real sneaky thing going on there because it's like, yeah.
Doing this, like, how much do you think, or did you ever draw or kind of think about a truth table that you might make in a logic class? The syntax totally messes me up. It's very hard to read.
Oh, yeah,
It blocks my thinking. But when you see a simple kind of truth table, right, where you write, TT, FF, and you do all of that, that logic becomes very simple and kind of easy to understand. And when you think about not, you just put the little, kind of kind of curly thing in front of it, and if you think about the and or the or, right? Those become very simple and easy to understand. So kind of when thinking about this, the syntax blocks me, but that idea is very easy to understand.
Mhm.
So when did you look at something like that when thinking about this, or what was your kind of
The answer is yes. I mean, I've seen logic from math classes. I think the difficulty, at least for me, is how do you bridge that to this world where the only thing that you have is a single argument function?
But that
like-
truth table is a single argument function, right? It takes in a 1t.
Right, but how do you encode it? That's the there's you get in the x and the y, but how to take the logic table and actually turn it into something that I can type within the rules of what I'm allowed to type becomes really challenging, because there's no if statement. There's no control flow or anything in this. The only thing I can do is function call. So it becomes this really weird puzzle where it's how do I do this when the only operation that I can do is call a function. You're exactly on the right track though. I mean, if you're looking at this thinking if that is insane, I never would have come up with that. I mean, that is totally the correct response to that. Don't ask this on any job interview question, by the way. Just yeah, I mean, no, that's it's sort of crazy. The or operator is also kind of this a similar thing. I mean, or. I don't know. What do you think for that? Well, think about the or logically. If the first argument to the or was true.
Yeah, you just gotta switch the order of the x and y to reverse.
Yeah, to do the or.
Yeah.
Yeah, if x was true, then you're done. It's x. So the behavior of or is if you're true, it's true, right? If x is not true, then it must be y. Whatever y is, and you'll get that. So or true and false is true. Or false and false is false. So you can build it up, but it is sort of it's tricky. It's not. I would not claim that this is obvious. So if you've never seen this before, it's whoa. So.
Yeah, so I just tried this, but or false and true comes out with problems.
So or false and true comes out with.
Oh, really? Huh.
Yeah, that should be okay. So. Yeah, debugging some of this is a real challenge sometimes. Yeah. All right, did everybody get that code entered, by the way? Just trying it out. Again, a lot of the code in here is something that's try it out, and then you sort of stare in disbelief that this shouldn't be working, or it's sort of nuts, but it is kind of, I do think it's kind of interesting though, where it's we basically started with nothing, where it's you have functions and substitution, and now all of a sudden we have Boolean logic. It's the thing that, again, it's a little strange, is that there's nothing concrete here again. It's there is no bit or data structure. It's all purely behavior, basically. The behavior of or is that, well, if the first thing has the behavior of true, then the result of or is the behavior of true. I mean, it feels sort of very kind of nebulous and abstract.
So, at first you started, you can only have kind of a single argument function, right? But then you made add with the kind of two function calls, right? So we can then infer that we could have kind of an infinite number of function calls, right? Mm-hmm. So technically you could take any number of things, right? And so if you wanted to represent something, say you wanted to represent a simple kind of three-letter alphabet, right? You could just have each bit, so to speak, be some n number of function calls to represent a string in that alphabet then, right?
You are exactly right. And you're actually on to the very next thing we're going to talk about, which is how would you represent numbers? you want to represent like integers or something. Like, let's forget about letters per se, but let's say you were thinking about numbers. And one thing with the numbers is to maybe not overthink the numbers, but to go back to kindergarten. Okay, so like how do they teach like preschoolers how to do numbers? And it's like there's a lot of like finger counting kind of stuff, like 1 and 2 and 3, and then they show you pictures of like, well, how many gummy bears are there, and how many, it's always showing like a visual representation of like a certain number of things, and or maybe you do like score marks or some other thing. And if you wanted to do numbers, could you do something like that with functions? And the answer is actually yes. We had the comment up here. It's like, since you can have like an infinite number of function calls, maybe you could use that for numbers. Let me show you one of them to give you kind of an idea. Like maybe 1 is where you do one function call on x. Like you say f of x. I call the function once. That's the number 1. It's like a repeat. And then maybe the number 2 is like 2 function calls of x. Like you just say f of x. It's like holding my fingers up where it's like 2. Okay. What would 3 be? Big quiz time. What is 3 in this universe? Yeah, f of x. Now, you're going to look at that, and you're going to say, like, what is that? Like, I mean, okay, so it's like, again, this is like purely, it's like functions all the way through, but like, what is going on here exactly? What the numbers are representing, again, is a behavior. It's not a thing. It's not a bit pattern or anything like that. The behavior of 3, for instance, means that you take a function, f, and you call it like 3 times on some, like you start with f of x, and then you do f like 3 times in a row. Let me show you an example. Let's say you had a function increment. Again, this is not allowed in our rules, okay? So this is like legal in the rules, but this is just purely for like demonstration purposes here. Basically what the numbers are is if I said incr of 0, that's like the number 1. I did incr 1 time. If I did incr 0, that's 2 times. I did incr 2 times. And then if you said incr, like if I started doing it like a whole bunch of times, I mean, essentially it's like repeating that function basically a whole bunch of times. Essentially what we've got up here at the top is an abstraction of that idea where instead of writing out like incr like that, I could just say 3 incr 0. And it would do it. It's like 3, basically you give me a function and a starting point, and it will just like turn the crank like that many times, like 3 times. The thing that's really odd about it is it's all extremely abstract. It has like the number 3 does not actually care what the function is or what the x is. It's like a behavior where it's just like, I'm going to turn the crank 3 times. I don't really know what it is, or I don't even really care what's going on. I'm just going to turn the crank three times on it. I mean, just as something wildly different here. I mean, I could have a function p that maybe this thing takes we'll introduce like Python tuples or something, just to do something really radically different here. Like here's a function where you give it like a tuple, like 0, 0 or something, and it increments the first value, and so forth. You could do that. Like you could say, well, what's 3 of p applied to the tuple 0, 0? Then it comes back with like 3, 2. I mean, essentially it's just like turning, like the numbers are basically just like turning the gears without any regard for what the actual function is. As long as it's a function with single argument. Okay, we're still in the single argument case here. Okay, let me put the code back up. let me see if there are questions here. Let's pause for a second. I do want you to enter that code and try it out here.
So if we're, you said there were no exceptions in there, right? But seeing as how you're starting to do math, right? If you get to divide, what happens when you divide by 0?
We haven't even gotten there yet. We don't even know how to add yet. We don't have to like divide. I mean, are you like, that's like in the next version or something. I mean, we don't. No, but it's like all we have now is just like a representation of numbers. Like okay, the number 3 and 4. You know, like I mean, we can type them out. We're actually hitting a bit of a problem here, which is like, how do I get more numbers into my system? I mean, do we just make like a big file with like the first 1 million numbers in it and then like type it out? I mean, that's a little bit weird. There are some other kind of interesting things going on as well. What if you were to do something like this, like 4 of 3? I don't know, like what if you were to do that? Remember that a number means that you repeat something a bunch of times. So what I did here is I just said, well, I'm going to do the 3 function 4 times. No. Let's try it, like a increment 0. I don't know, what do you think the result is there? Any 12? 81, yeah. What that's doing is it's doing exponentiation. It's doing 3 to the 4th power. Like 3 means do something 3 times. So if you do 3 times 3, that's 9. Times 3 is 27. Times 3 is 81. Yeah, at some point. Yeah, but already, like, just from that, you're maybe getting a little bit of a hint of some mathy stuff where it's like, okay, this is weird. Like, okay, like the behavior of 4 is to repeat something 4 times.
The part of this that I am following is when I see the 1, the 2, the 3, and the 4, is those things are creating function objects in Python. And they're
Yes.
unique objects, and they represent unique things, which we've happened to name 3 and 4
Yeah.
and 2.
Yeah.
So is that helping me or making it harder for me to understand the rest of this? And we have names too.
Yeah, I have to name them something just to even refer to it at this point. I mean, the thing that I want you to focus on is that they are functions. Okay, so Lambda defines a function, and this is a function that returns another function. I'm gonna be stretching you on the syntax a little bit here, but it's like this is a function that returns another function, and then what it's doing is it's just doing like f of f of f of f of f like a bunch of times, and then the number of times that you do that is what the number is, how you're representing the number. It's like, and again, it's like finger counting, like from kindergarten, just in a really horribly gone astray, basically. So but it's the same idea there.
I was thinking until we typed in 4-3 that you could make some sort of a 10 and hundreds kind of a thing, and then you could do 10 of 3 and it would be like 13, and that's how you get more numbers in. But I haven't quite figured out how to do multiplication yet because I really thought 4-3 was going to be 12. Right, I thought that was going to be 12, so I'm lost. But
So in the syntax that you use, where you do like the 1, 2, and 3, you have a lot of kind of nesting going on. But it looks a little clearer to me when you write things with just, kind of where you did a inker 0, right? So where you have like the single argument in each of the parentheses, right? So if you took something there and you just had some long, like if you wanted, like you created the bit earlier, right? I mean, you could create, like a 4-bit representation of something with 4 of those kind of parentheses in there. And if you passed in true in the first one and zeros in the others, you represent some binary number, right? You could do 1 in each block, and right, you could combine them in all these sorts of ways where now you suddenly start having a bit.
Mm-hmm. I think you probably could do numbers in that way, but then I mean, you could go like down the binary route of numbers, but then you're going to hit like an upper limit at some point. Now you're writing binary. I haven't explored that angle, and I got to go down that direction, but I mean, I could see going that way. Yeah, this thing here is something known as the church numerals, by the way, is kind of a name for it. There is a challenge, though, and we're kind of getting to it, which is, well, before we get to the challenge, there are some other challenges. One challenge is, how do you implement 0? That's a picture of the black hole, by the way. It had a bunch of Python code involved. I thought I'd include that there.
To be clear, our universe here doesn't have none, it doesn't have pass, it doesn't have any sort of null concept, right?
There's no null concept, no. Yeah. The thing with the 0 is that, first of all, there's an API for numbers. Not to talk about APIs in here, but the API for a number is that you take an f and you take an x. If it's not that, it's not a number. Okay, so it's like there is a very strict protocol for what numbers are going to be. The other thing. Oh, by the way, I'm getting kind of tired of typing the Lambda. By the way, so I'm going to use Lambda. I realize that this is not going to work in your editor, but you're going to have to do a little. I'm going to require you to do a little mental substitution here. So I think the key to a good tutorial is to use a custom environment. So we'll come to that in a second. So the 0 is basically going to be lambda f, lambda x. And the question is, like, how would you represent 0 in this system? Well, 1 is like 1 usage of f, and 2 is 2 usages of f, and 3 is 3 usages of f. What do you think the 0 is?
0 usages, right?
Yeah, x. Like you didn't use f at all. It's like you just gave me an x, and it's like, okay, you didn't do anything to it. So like the 0 basically means you didn't do anything. So if I said like 0 incr of like 0, it means you just stayed at 0. You didn't call the function on it. So where this is going next? Question in the back there.
So does this mean that 0 and true are equivalent?
Yes.
Okay.
They have the same behavior. I'm not going to make that association because I'm already quite confused as it is. And like, I'm going to try to keep 0 and true as different things. But yeah, you will notice that the implementation of the 0 is exactly the same as true. No, wait, it's the 0. It's the implementation of false, actually, right? Because like the behavior of false is to pick the second thing. So here we're picking out the second thing. We're picking out the x. Let me clean up a bit while you're thinking about that. Okay, so I got 0. The thing we're going to look at next, though. Okay, question over here.
So it's impossible to implement numbers without the incr function, right?
The incr function is a side of, like, that is a Python thing used only for illustration.
Okay.
Yeah, so you can actually see the number. No, so the strange thing about, like, if you look at if you look at like 3, it just comes back and says, I'm a lambda function. And then it's like, it's purely abstract. Like, it's like, what is that? Like, and like basically the concept of 3, it's a function that does something 3 times. And in order to see the effect of it, I have to provide a function for it to look at. I mean, I could write different functions, like here's one that adds like a star to x. Maybe we do like strings or something. What would happen there is if I did 3 of f and then gave it like an empty string or something, it's like essentially you're giving it like the starting point, and then you're like, the 3 represents like turning the crank 3 times on it. I think it's really hard to kind of mentally like wrap my brain around this, because there is nothing sort of concrete here, right, which is really sort of weird.
In each case, though, you're giving it like an empty value as like the second argument. Is that just to give it? Is that because it's a natural starting point?
Yeah, it has to kick off with like an initial value.
Okay.
Yeah. Now the thing we're going to look at next, like just kind of push forward a little bit here. What if you did want to do math with this thing, like add and multiply and other stuff? One of the problems is that you have all the numbers hard coded, at least so far. Like I've just been typing them in, and it's like, well, that's just terrible. It's like I don't want to do that. And then the question is like, well, how would you go beyond that? And it actually takes you kind of into this thought of like, well, what is the most minimal thing that you need to do math? The picture up here of piano, there are these the piano axioms from math. They're maybe a little bit abstract, but the way that they're kind of phrased is they start off saying 0 is a number. And then you get into all this talk about creating successors of numbers. Like if you have a number, can you get to the next number? And then could you build math by just being able to get to the next thing? Basically the act of counting. Like if you can count, like go from the number 2 to the number 3, can you start doing like more interesting math operations? And the answer is yes, but the challenge here is implement successor. Like, can you write a function that would take a number and then get you to the next number? This is typed out as suck, by the way, S-U-C-C. So yeah, so we're gonna have a function successor. As input, it is going to take a number. And again, you're gonna have to sort of mentally translate my Lambda character into Python, by the way. It looks like that. Okay, so everywhere you see the Lambda character, you're gonna type Lambda. And the question is, what are we gonna do here? So just to make sure we're clear about what's going on here, if I say successor of 2, what's gonna pop out of that is basically 3. Or that's what we want to have happen. So, so we're gonna have this function that basically takes a number, and it's gonna have a number coming out. And so the question is, how is that gonna work exactly? You are correct. One more function call. One more function. No, you are absolutely correct. It is one more. It's like Spinal Tap, right? You're at 10, and you need to go one more. You go to 11, right? You know, that's the famous scene. You're going to have one more function, but before you do that, you have to sort of think like, so what is this successor thing returning exactly? It's returning a number. And the critical thing about numbers is they have numbers have a very specific API. Think about the API to a number, not to bring API into class, but the interface to a number is that there is always an F and there is an X. That is the API to a number. And it turns out that that is what you're going to do here. Maybe parentheses might help this out a little bit. Like basically, you're going to be returning a number. It takes an F and it takes an X. Okay, we're gonna return that. We're gonna use your comment, which is exactly correct. You're gonna do one more F. That's go to the next number, you have to go one more. So there's going to be an F out front, which is the one more. But then what is gonna go in the parentheses here? So the behavior of a number, right? It's like a number, you basically give it an F and an X, and it repeats that many times. So this is basically the old number here. Okay, so that's the old number. And then we have the extra F on front. That's taking us to the next number. So if I were to say successor of 4, for instance, it's gonna come back with this crazy result. It's gonna say, okay, function lambda. And you're like, what is that? Well, if that is working correctly, it's a function. And so I'm gonna use my magic underscore variable here. I should be able to pass that like inker in 0, and it'll come back saying, oh, it's 5. The successor of 4 is 5. So if you use that, you're getting 5. Okay, now just to see the syntax of that written out, I did anticipate this problem, by the way. So, so I'm going to leave that.
What do you think about doing it as a def? Does anybody else want to see that? Or am I the only one?
Yeah.
I really like this kind of syntax because you have that lambda symbol, and then you have. I really like the syntax because you have that lambda symbol, and you have the word lambda. But we began the talk with the idea of substitution, right?
Yeah.
So you just take that symbol and you substitute this other symbol into it, and then it just kind of works.
Yeah, I'm just doing it because I'm lazy. Yeah. Yeah. Now one thing. Now your comment on the notation, like I actually am doing something very deliberate here, which I'll get to. If you read papers about the lambda calculus, they tend to use very cryptic mathematical notation with the lambda character and other stuff. I am steering you a little bit in that direction. So at this point, this is basically Python code, except that I have replaced the lambda word with the lambda character. If you must know, my editor is literally doing like a string replace on it. Like, I mean, I have a custom environment. It's taking my code and it's just like, oh, if you see the lambda character, just replace it with the word lambda. So it's a notational shortcut there. If you're done with that, by the way, I'm going to give you the challenge of implementing add and multiply. While we wait a second here. Yeah.
A successor, do we have a decrementer? Can we go back? So,
We
like,
do not,
subtract?
and I'm not going to address that question right now. But it is something to think about, which is like, how would you go to the previous number?
Like unturn the crank.
Like, yeah, how do you undo a function call? That seems like a really weirdly tricky, kind of crazy thing. And I'm not going to address that right this second. So.
To comment on the underscore method, so everybody's clear, including myself. That's just a helper, so you can not call successor for incrementer 0 kind of thing.
Yeah.
Okay.
Underscore is the result of the last thing you do in the REPL.
Perfect.
In Python. Like if you've used like Jupyter or the Python REPL, the underscore always holds the last result of whatever you did. So I'm using that here. So the result of the last thing I did was the like here was the successor of 4. But you could do this kind of stuff. Like you could say, do the successor of 4. Like do it twice, and then pass in the inker function in 0, and it would come back and say, oh, that's 6. 2 successors of 4 is 6. That last example, by the way, is giving you a hint on how to do add. Well, say you wanted to add 2 numbers, like you wanted to add 2 and 3, and you wanted to describe this again to like a kindergartner or something like that, and you wanted to do it with finger counting or something. You could say, well, if you had 2, you want to add 3, you push up like 3 fingers. It's like 1, 2, 3, and then you look at how many you have. Basically, you just did 3 successors of 2. Like 2 and 3 is 3 successors of 2. And you could do that. Like basically the way that add would work is you would take y and you would say apply that, like take the successor function and apply it a whole bunch of times to the other number.
So when I learned math, like there's a certain way to kind of think about it, but I mean, there's the other idea, which is that multiplication is just repeated addition, right? And exponentiation is just repeated multiplication. So you have these things that are kind of nesting or just like repetitions of themselves, right? So now that you can add 1 to something, which is why the Italian guy for his name, but he had to start somewhere. So he started with 0.
You start
and he
with
said
0.
You could add 1 to something.
Yeah.
And if you can just do that some infinite number of times, you can get
Uh-huh.
anything.
Yeah, yeah. So that's kind of what's going on here. It's like once you have the successor function, you can start using that to get to different spots, right? So if you have like 2 numbers, x and y, and you wanted to add those together, you would take like the second, like if you had 4 plus 5, you could get to 9 by doing 5 successors of 4. Like if 4 is your starting point, and then you turn the crank on the successor function 5 times. So add ends up looking like this thing that I've got here. I'm going to put up the Python syntax for that again, just to. I'll have you try that out. Yeah, we'll get to that later. Yeah. What, you want to be able to use the Lambda in your Python code now? What, the custom environment? Nah, nobody wants to know about that. You're better off not knowing, yeah. Multiplication is something that you can also do. In the interest of time, I might just kind of show you what that looks like, and we'll leave it as what it was left as an exercise to the reader to fully grok that. Basically, the way that multiply works, like imagine that you have like 3 times 4. What you do with multiply is you're going to take the function, like you take one of the numbers, like x. X is one of the numbers, so like that's like 3. We're going to do 3 repetitions of f. Oh, yeah, yeah. And then we're going to do that y times. Well, you try this out here. That one is maybe, honestly, this one is something that I have found very difficult to kind of wrap one's brain around, is the multiplication. It's essentially you have a number x, and like what is the behavior of x? It's like a repetition. So if I have a number 4 and I give it a function, then x of that function, that means like doing f 4 times. That's what that means. And then if you put this y out front, it's like you're repeating that 4 times f like 3 times in a sequence there. It's a little weird, but...
The thing that breaks my brain about that one is that it has an f, and add doesn't. And I feel like, I know that f is coming from the outside and that we are calling f underneath, but that's what, I was like, wait. Like, that's what killed me. Not that that's a useful comment, but that's
I
where
would
it lost
agree.
me.
I would agree on that. Yeah. All right. Did that answer your question? You had a question. Okay. Is anybody's mind like fully shattered here a little bit? I don't want to dwell too much on the exact implementation of that. I think maybe the kind of interesting thing here is that we have kind of bootstrapped ourselves out of nothing, like this idea where it's like, oh, all you have is single argument functions, and you have nothing else, and like all of a sudden we can do math. Like we have not violated any rule here about any of the functions. It's just like pure functions. And it's like we have this behavior of math. The thing that's really unsettling about it is that it just feels like really abstract and strange. So there is that. Yeah.
Could it be rewritten with the add that was just made? Or it still breaks things because it has...
The sole purpose of the inker function is for me to actually show to actually visualize what we have here, because everything is basically a function. Like if I were to say something like mul 4 times 3, it just comes back and it's like lambda. And I have no way to visualize that as a number Because what that is it's like a behavior, basically. It's like, that's a function that has the behavior of doing 4 times 3. And I can't view it unless I apply it to something. Like, I have to do something with that to actually see the effect of it. So the inker function is actually not needed. It's not really part of what we're doing, but I need it to actually just show you like the result of the thing. So
would it, for this, then make more sense to define a print function that just applies inker and 0 to something?
okay, we could do that. Sure. We could do like, I don't know, show n or something like. Again, this is Python. I mean, like, we do not have a print statement in this Lambda calculus kind of world here. But this is just like debugging only. But you could do that. I mean, what would happen there is you could then say, like, show the last result just to debug it. But no, it's really hard to kind of debug this stuff if you're not on top of it. So.
Try writing equality.
We could try, but I would not be successful. Yeah, it can be done, but we'll get to something similar to that.
I think this is kind of interesting because when I look at what you've written there, which is multiply 4 and 3, right? Multiplication basically takes 2 arguments, right? I mean, you've written it as it takes kind of single arguments, but my mind just drops the middle parentheses and substitutes a comma there, right? So multiplication definitely seems to be a behavior to me, right? Like, it's a little machine that turns some crank, right? 4 and 3 represent numbers, which kind of feel like state. But you've defined them earlier.
They're also behaviors.
As behaviors, right? But it has to go back to 0, which is also actually a function. So 0 itself is a function, but it's kind of the initial state starting point, of which inker is then your kind of grounding, like, machine.
Mm-hmm.
So I'm seeing f here as like a generate starting value thing where you're shoving inker 0 into that, right? If you just plugged 0 into that, would it still work?
Like
instead of
zero,
inker 0?
Like here? Like that?
No,
Or-
I mean, sorry, the numeral 0, just for the debugging.
Oh, that?
Yeah.
It would blow up because it's not a function.
Okay.
So if you did it, well, I lost my. Like, if I tried to do that.
What if you did?
It blows up because it's basically trying to call that as a function.
What about inker of like -1?
Same thing.
Same thing.
Yeah.
Okay. Okay. Thank you.
Actually, no, I don't want 0 there. I want the inker. Yeah, inker there. All right. Now I do want to do one little digression here. You're gonna indulge me for a second here. This thing that we're doing with the numbers is a little weird. Like, well, maybe a lot weird, actually. I mean, like where you have like the chaining of operations like that. And I was trying to think of some way to bring this back to Python in some capacity. And one example that I was thinking about was maybe the JSON object from hell problem. Okay, probably people do stuff with the web, right? And you get a lot of dictionaries, and it's like dictionaries upon dictionaries and all this kind of stuff. And what if you wrote a function, like you had a function like get C, where you gave me a dictionary, and then what you were trying to do is kind of like navigate down into that. Like that, get C of data. Essentially what it's doing is it's like navigating down into nested dictionaries. That thing that you're doing there is kind of the same as this function thing of repeated application of some operation. Basically, you do the get on the outer dictionary, and then you take the result of that, and you do the get on that. And you're kind of like progressively like going down into a bunch of dictionaries. Do people see that? Yeah, question in the middle.
I thought you said this wasn't going to be relevant for work.
Oh, you'll see in a second. Yeah, good. No, I'm going to make it irrelevant in a second here. Okay, so you have this chain. Okay, I've had code like this that have to deal with. Like you have the chain dictionary thing, but one of the problems that you sometimes run into is that people give you malformed data. Like maybe they just give it an empty dictionary or something, and then all of a sudden you start getting key errors like all the way down. So it's like, oh, okay. So I have this dictionary, but like the item might be there or might not be there. And one of the things that you might do to fix that is to do a bunch of like if statements or some crazy thing like this. I'm going to write something out. You're not going to like the code here, but. We're going to have like a horrible code review later here. But you might write something like this, where it's like, okay, I have this getC function where it will go down into a nested dictionary. But if you give me like a dictionary that does not have the data in there, it's not going to blow up because it's using like the get method, and it's trying to basically play defense a little bit. Does everybody see that? Okay, what is your thought on this code that's in there?
And I think D is not a very good name.
Yeah, D is not a good name. One thought is just this none check. Yeah, well, yeah, I'm assuming types. Yeah, we should have gotten rid of those. But yeah, no, there's like assumption of types. But one thing that's a little weird is there's a lot of like code repetition kind of going on here, where it's like, I do the if check, and then I do the get, and so I'm going to do a little trick on this. I'm going to write a function called perhaps. You're going to love this, where you give me a D and a function, like that, and then what I'm going to do is I'm going to check the D. Basically, if D is not none, then I'm going to return the function applied to D. And if it is, then I'll just return none back. So I'm going to write like a little helper function like that. And you're saying, where is Dave going with this exactly? Okay, so here's how this is going to work. You would basically say like perhaps data, and then you would give it a function. I'm going to use Lambda here, just because we've been doing Lambda so much. We'll do that. So the idea is like, you give me data in a function, and as long as the data is like a not none, like a dictionary or something, I'm going to call the function. If you were to try the same thing on like an empty dictionary, it just comes back with nothing. Where it's like, oh, well, the empty dictionary didn't, well, actually, it would have called this, but you're just getting like the none back. Okay, so I'm writing like this little perhaps function. And maybe I could start doing some chaining with that. You're not going to like this, but.
Can we, after you're done with this, just see data again for 1 second?
Oh, the data's that. Okay. I'm doing this like crazy kind of function where it's like you give me a piece of data and you give me a function, and it's basically it's like, well, I'll only call the function if the data looks good. Like if I can move forward, I'll try calling the function. And so you could start like chaining this stuff up. Now this is where it's going to lose relevance for work, right? I mean, somebody made the comment. It's like, oh, I actually could use this at work until we started doing this. So you maybe you've got this whole like chain of stuff going on. We're going to see if I can actually type that in. Okay, so this is like a totally different formulation of this thing. I got this like perhaps function, and then I have this like this callback or something, and it's like it's just chaining the thing. It's kind of like what we're doing with the numbers, right? You know, like the f of f of f of f. Here it's like perhaps, perhaps, perhaps. It's actually like the song. I don't know whether people know the song. There's like a famous song where it's like perhaps, perhaps, perhaps. So you're doing that. You might look at that and just say, well, that is completely nuts. Like why would I type that in? Everybody, how our heads here. I'm going to fix that by introducing a class. Classes are not part of the Lambda calculus, by the way. This is a digression. Okay, so I'm going to introduce a class, and then as one does, we're going to do operator overloading. And we're going to do the check here. Where we do a little bit of magic on it. What this is going to allow us to do, and let me pull the slide up a little bit here, is you're going to be able to do perhaps data, and then start chaining it through a bunch of functions. Oh, you get an object back. And then the value has the 42 in it. So you end up with that. There's going to be a quiz on this later here. In some sense, this is kind of an extension of the number idea. It's like you're turning the crank, where it's like you're taking like functions and you're like applying a function one after the other, except that you've got this like extra weird like little check in there. It's a little weird. Your probably job security would go up substantially pulling a stunt like that. So the reason that I've done this, you're like, where is he going with this? I guess my only comment on this is that perhaps this is a monad. If you've ever heard that term kind of floated around by the functional programming people, it's very difficult to kind of pin down what it is. And this is an example of one. So if you've ever heard that, it's associated with like turning the crank on a lot of function composition and other things. I am carefully choosing my words here because perhaps this is an example of a monad. I've been very careful there because like anytime anybody tries to define monad, they get like about 1,000 people coming on Hacker News and pouncing on them to tell them how it's wrong. So I'm fully expecting that, but I'm choosing my words carefully here. Like if it ever comes up, if somebody says anything about monads, you could just say, oh, it's like the song. You know, the perhaps, perhaps, perhaps song. And then they'll probably get like even more angry and, you know, who knows here. We do have to do the break in a second, so we're gonna do that in a moment.
Can you repeat what you said the API was? Something takes what, a function and a number?
For which part? The perhaps thing?
No. I mean, just kind of earlier, you said we had one basic API, right?
Oh, for numbers. Yeah, numbers, it's always a function and a starting point.
Function and starting point.
Starting point, yeah. All right. We are going to do a break. When we come back, we're going to do, it's going to get even more insane. Now, when we come back, we're actually going to talk about how to do something that looks like computation with this. Like, can you write things like recursion and loops and other things? We have to build a little bit of stuff up for that, but let's do a break. So I think we're breaking until 10:45, I think is the end of the break. So. We'll get started in about 3 minutes here. So. And we'll start in a second here. Everybody's ready for the post-break quiz, right? Isn't the All right, I'm showing 10:45, so I'm going to continue here. Got a fair number of people back. That's good. Okay. What we're gonna start with is I actually wanted to do a little bit of discussion, maybe about some of the history of this and kind of what we've been doing in the first part. And the first thing that I actually wanted to talk about was function definitions a little bit. One thing that I kind of stepped you through in the first part of the class this morning is this idea of defining like nested functions. Like we had the AND function, which I think looked something like that. But what was happening in the first part of the class is that some of this was actually getting shortened down. Like I was progressively using things like the Lambda function instead, like, instead of doing that, you could say, well, return like a Lambda function. Or you could write the whole thing basically as a Lambda function. Like that, basically, just sort of making it more compact. One thought that you can kind of explore is just what is like the minimum notation to specify what I'm doing here. Like you're writing functions in different ways, and like the def format is what you're probably most familiar with as Python programmers, but then taking it down to lambdas, making it more and more compact. And then I started doing stuff with my editor where it's just like, I started using the lambda character. You can start asking questions like, can you take it even further than that? And the answer is yes. I mean, like one of the things that you could do with this is you could look at parts of this where it's like, if you have two lambdas like in a row like that, you could just write it as one. That's another syntax for it. You could also look at some of these things like these things at the end are basically chained function calls, like x is applied to y is applied to x, like that. You could just get rid of the parentheses. And then as a final step, you could just get rid of the colon too, because one dot is clearly easier to type than two dots, right? Okay, so, so you could write the code, I mean, like that. The reason that I'm showing you that is that's the syntax that you will see if you start reading papers about lambda calculus. They tend to use like this very mathematical syntax, and essentially all of these things are basically the same. I mean, like this last thing, this is a function that takes 2 arguments, sort of one at a time. I mean, it's kind of hidden, and then it's applying x applied to y applied to x. Like if you wanted to see the Python code for that, that's what it is. I mean, it's literally Python code that's doing that, but it's been written in sort of a highly compact way. So so if you do start, you start looking at again, Lambda calculus, you're going to see this kind of use of symbols, basically. So
the question I have is pretty useless, but I think it's in the spirit of the whole exercise we're having.
yeah.
But it's great, by the way. Really, I like it. Using this syntax, can x and y be more than 1 character, or that's a limit?
Usually in the Lambda calculus, the variables are 1 letter.
Okay, so you only have like 26 or something like that?
Yeah.
Okay.
Yeah.
You could just use all of Unicode.
Okay.
I think actually in the Lambda's calculus paper, they say if you need more, you just put like bars above it or something, or subscripts or something. It's a math paper, so they kind of go in the math thing. But as written though, it's like we have 26 variables. You don't need more than that, right? I mean,
So when I think of the word calculus, and maybe this is an incorrect or incomplete kind of understanding of it, it's generally understood as like the study of the rates of change. Is calculus in here meaning anything about rates of change, or like what does the term calculus mean when they say lambda calculus?
It has nothing to do. The question about it has nothing to do with calculus as you would have learned in like high school or anything like that. But your question is actually onto something else. So part of what you have in this lambda calculus is a certain like I don't know, symbology, if you will, where it's like this is a way of writing a function. Like you have x and y are variables, and lambda means you have a function, and variables next to each other means that you're calling functions and so forth. But where the calculus part of it comes in is there are a bunch of conversions that take place on these like lambda expressions. And then there's actually some things that you can do with functions. So I'll kind of go through some of these rules. One rule is that you can rename an argument. Let me illustrate that. So let's say you had like lambda xy, xyx. You could, if you wanted to, just change one of the variables to some other name. This is something you can do this is something you do in the IDE, right? In Python, right? It's like, oh, that was a dumb name for some variable. I'm just going to change the variable to some new name. You can do that. So that is one rule, is you can rename arguments. There is a caveat: you can't introduce a name clash. So like if somebody was already using the variable z for some purpose, I can't just rename x to z. It's like, so you can rename things as long as you don't introduce a clash. This is something known as alpha conversion. If you kind of read papers on this. Another rule is that you can substitute argument. So let me illustrate that. So let's say you had like some lambda expression like this, and then you applied it to some value like AB. This is literally like a function call, although it's like obscured by all the lambdas and stuff. It's basically what you're doing is you're saying, okay, take all this stuff and now pass like AB into it. Basically what the substitution rule is saying is that you could take like whatever is like in the parentheses there and substitute it in for the x. So you could rewrite this basically saying, okay, this is lambda y, and now I'm going to put the AB in the place of wherever the x is, I'm going to put AB in there. This is kind of the essence of like a function call. Like if you apply a function to arguments, essentially you can take the argument, you can stick it into the function like that. Yeah.
This is a little bit of a digression. Could we see the notation for multiply? I'm curious about the sort of the nested parameters. Do you have to keep the parentheses, or what does that look like?
So let's see, where was multiply here?
It was, I have it up if I don't know if that's helpful.
Like that. I think I think you actually do need the parentheses there. There is a notion of like precedence. Like sometimes you need to like group things in a certain way, and like parentheses are still used to do that. So like if you need to group things like in a certain way. Yeah, so no, the parentheses do actually have significance. So, yeah.
You said it was lambda y, but where does that first y come from there?
Oh, so the y, so no, you're on, so the y, this is where this thing gets really confusing. Here, there's only a single argument, which is the AB. And it turns out that the AB went in as the argument x. And because it only went into the x, the y is remaining. There's like a remaining argument y that needs to be provided. If you had like a second thing out here, like z, then that would become the, like what you would have is the y would basically go away and you'd have like the z. So the reason that was basically like a lambda y there is I only gave one of the argument. I don't want to dwell on this too much, like the substitution thing, but just the gist of the idea here is that you can basically substitute the arguments. It's like you literally take the argument, you just paste it into the thing. There is also a caveat on that you can't introduce name clashes. Also with that, here's kind of a weird example. Like let's say you had lambda xy, xyx, and then you decided to pass in like xy into that. This is like a really mind-bending thing because it's like, is that xy the same as the xy that's in the function? Let me give you a Python example of this. Let's say you had a function like f of xy like that. I don't know, maybe, I don't know, 2 times x plus y or something. Okay, we're in the Python world. And let's say you had like an outer x and an outer y like that. You run into these, it's basically scoping issues. Like, is the outer x the same as the x in the function? No, because it's like x was basically an argument that got passed in. Though, like the global x's and the local x's are different. Like the xy are different. That is the same thing that's happening here. If I have a function that takes x and y as an argument and does something with it, any like xy that's outside, that's actually a different xy. And you can actually run into like really weird problems with that. Actually, maybe like a different example of that. Like let's say I were just to pass in y there. This does not get reduced to lambda y, y. Like it's like no. Okay, just put no like that. The only way that you can actually fix that is you have to rename one of the variables. That's actually what the first rule is about. It's like if you want to do that, you would have to rename one of the variables, and then you could do the thing. Like that. Again, I don't want to totally dwell on that, but that's another, this is getting back to your question, how's the calculus kind of coming into this? This is sort of it, where it's like you have this symbology here, where it's like you have these lambda expressions, and you can replace variables, and you can substitute things. So one of the other things that you can do, let me just tell you what this is. This is like beta reduction is what this is called. Oh, x, oh, yeah, good. Yeah. Okay, yeah, good catch there. Yeah, the debugging is always a little difficult on this. So you have rules like that. There is kind of another rule that is, well, I'll do kind of a simple example of it. One rule is that you can make a function. So let's say you had this x equals 3 just sitting there in your Python programmer, and you really wanted to annoy people with it, like at work or something. You could take that and just turn it into a Lambda function that just had 3 passed into it. I mean, I don't know why you would necessarily do that, but I mean, like you could just say, oh, I'm going to make a function, and then I'll pass in the argument as the value of the function. And you're going to end up basically back where you started. Think of it as like gratuitous obfuscation or something like that. That's another thing that you can do with this is like introduce functions or like introduce like a variable and so forth. And so so if you look at some of the papers on some of this stuff, they actually talk about like these substitutions. So this is a slide from the Lambda calculus book from 1941. And he's sort of talking about these rules, basically. Like you can replace parts of formulas with like name substitutions, and you can. It's talking about basically symbol replacement, like substitutions and so forth. And one of the reasons why this is talking about this, you say, okay, so where's it going exactly? You have this kind of weird symbolic system and these rules for kind of replacing things. Is that in the early 20th century, there was a lot of discussion about the nature of math. Specifically, could all of mathematics be derived solely from like symbolic manipulation? Like if you had like the proper set of axioms expressed in symbols, could you derive all of mathematical truth from that representation? So there's a whole school of sort of formalism in math. It's like, formal systems and axioms and all this stuff. David Hilbert was one of the main figures of kind of at the center of a lot of that, basically, posing questions, it's like, can you decide any math problem by just turning the crank on like a symbol manipulator? And nothing, no creativity at all. Just like if you had the right set of axioms, could you just turn the crank and prove stuff by turning the crank? Would you eventually get to like mathematical truth from that? And there's a whole lot of stuff that kind of came out of that work. So one question that got posed, it is this question, like, can all of math be derived from a formal system? Like if you had a statement from logic, this is kind of a statement of a problem. Like if you had a statement from first order logic, could you write an algorithm that would just tell you yes or no whether that statement was true or not? It's kind of an interesting idea, right? I mean, it's like, wow, that'd be kind of cool, right? I mean, if you just specify a problem and then it's like Star Trek or something, like computer, tell me if it's true or not, that would be awesome. So it's kind of posing that question, is there an algorithm to do that? And the short answer is no. I mean, there's a whole bunch of stuff that kind of came out of the 1920s and 30s. One thing that came out was the incompleteness theorem. Kurt Gödel, I think, probably butcher the pronunciation on that. Sort of, there was like a result saying that you could not prove like statements about arithmetic within a formal system. So that kind of came out. The Lambda calculus. Early 1930s was kind of in that same school as well, basically proving that you could not have like an axiomatic system or you could prove these statements. So all the stuff that we've been doing kind of merged out of that. You can still buy the book. So this is the Calculi of Lambda conversion. It's kind of interesting to look at, but this is from 1941 by Alonzo Church. So it kind of talks about that. A lot of what's actually being talked about is just how do you mathematically describe the ability to calculate something? Like how do you mathematically describe an algorithm? That's kind of like a really weird kind of problem. Like, it's like how do you describe, like we all know what an algorithm is. It's like a step-by-step process, but like how would you mathematically formulate that? And like in some sense, Lambda calculus is really about that. Some other figures at this time, by the way, you have Turing. So there's Turing machines also around 1936, and then one of the big results is proving that Turing machines and Lambda calculus are equivalent to each other. Not going to go further into that, but just trying to put like some historical context to sort of when this took place and like what they were thinking about, and a lot of it was this thinking about math. Can you prove all of math through algorithms and other things, and basically showing that you could not. So So that's kind of some interesting history on it. Where we're gonna pick up with it here is talking about like programming. So about 20 years later, you have the creation of Lisp programming. I think 1960 is when Lisp came out. In the start of the tutorial, I kind of mentioned, it's like, well, everybody calls it Lambda because Lisp called it Lambda. And if you read the paper on Lisp, it's kind of like, well, why did they call it Lambda? Like, what are they thinking about? And as far as I can tell, the only real influence possibly is the notation of the Lambda. So the Lambda calculus paper actually is cited in the Lisp paper, but it's kind of cited in this way where it's like, well, we're going to use Lambda notation to define functions because there's some convenient features of that. The actual Lisp paper is actually talking more about AI. Like they're trying to build a system for like AI programming or some other thing. It has nothing. I was not able to see any other mention of the Lambda calculus in the Lisp paper, but they're kind of borrowing the notation for it.
So here it looks like they're doing a slightly different thing with the notation because they're passing two arguments in to they just kind of went their own way with it.
Yeah. Which you can do in Lisp. Like Lisp, you can write functions with multiple arguments. It's they're sort of thinking of Lambda as like a convenient way to encode functions and what are known as S expressions and other things. So the notation is sort of coming from Lambda calculus, but it doesn't seem like much else is actually coming from like Lisp is not doing all this like crazy like number stuff and encoding things in that way. So it's sort of an interesting connection there. And Lisp in some way is kind of an interesting jumping off point for what we're going to do next, because one of the things in Lisp that was very focused on was list processing. I mean, that's the whole name of the language. Like Lisp is short for like list processing, right? So one question that we sort of run into is, in this Lambda calculus world, is there any way to actually build a data structure? Like if, let's say you wanted to do lists, right? I mean, like, well, how in the world are you gonna do lists? So, is there any way to make like a tuple or a pair or anything? I mean, so in the Lisp world, there are some functions for building data structures. There's basically a function cons, which essentially builds like a pairing of data. And then there's a function car that gives you like the thing on the left, and then there's a function cutter, which gives you a thing on the right. The names, by the way, are taken from the IBM 704 hardware on which the Lisp was first implemented. So those function names are kind of weird, but there's this question. It's like, could you build a data structure entirely out of a function definition? And the answer is you can. I'm going to do this in Python in kind of a weird kind of way to start. But let's say you wrote a function like cons AB. One way that you could build a data structure is you could define like an inner function. I'm just going to call it select, where you pass in an argument and then you just check the argument. Like if it's 0, you return A, and if it's 1, you return B. And then you just return that function back. It looks a little hacky and weird, but like it actually works. Like you could say P is equal to cons 2, 3. And it comes back and it's like, well, here's this function. And then you would call the function with 0 or 1 to get the data that you want. You can do it. I mean, it's and then like you could write car as basically returning like P of 0, and you could write cutter of P returning P of 1. Don't do this at work. I mean, this would be a terrible thing to. I mean, your coworkers would sort of hate seeing this sort of thing. But it's kind of remarkable in a way where it's like actually it is kind of like a data structure. Just totally from function definition. Like I'm not using a tuple or anything there. It's like here's a function. It's got this weird like selector thing in in the middle of it. Everybody kind of see that? Now, where I'm going with this, you're saying, okay, where's he going with this? Didn't we do like a selector thing at the start of the morning? Yeah, the switch thing. We just did that. Like we did like the switch thing. Maybe that's how we build a data structure. Like, so instead of doing this like cons thing like that, maybe we can do it using kind of the Lambda thing. So let me pull up the slide a little bit. We're gonna have a function that takes in like 2 arguments. And then we're going to define a function that's kind of like our selector here. Okay, so we're going to have our argument s, and then we're just going to use it to select the 2 arguments. Now you're looking at that saying, there's no way that can work, right? Okay, so if I say cons 2, 3, it comes back and it's like, there's this horrible Lambda function. The way that you're supposed to use that is you would pass in like maybe true or false or something. Like if I said p of true, it comes back and it picks the 2 out. Remember that true is the thing that picked the first argument, right? So true is going to pick out the a, and false is going to pick out the 3. I don't know. Is that crazy enough? I mean, it's so you could do that. You basically have a data structure. Keep in mind that 2 and 3 are not part of this, but I'm just using it for illustration here. So you can say car of p. You could use your numbers here. Yeah, we're not really using the arguments. We're just storing the argument. Let me pull it up again. Okay, give you a second to kind of type that in there. I think this is actually a really mind-blowing idea where it's like a function can build just from a function, you can create a data structure sort of out of nothingness. You know, it's like keeping, like this is not a tuple, it's not a list, or, you know, I'm not storing any kind of data in any sort of thing that you would recognize, but it's just pure function. Yeah. Although we could link them together, right? I mean, if you wanted to have like if you wanted to make like a linked list or something, you could do you could do cons of 2 or 3 or something.
A kind of question about language. You know, I don't know in the papers what terms they use. Maybe they use Lambda or something. But do you know when the term function got introduced or how that came about?
I have no idea. I mean, function's been used in math forever, so. Yeah, I'm not sure the history on that. So.
I mean, I think one of the interesting things here is, you know, when I think in a beginning programming class, if they talk about a function, they'll often refer to it as a machine. And they'll draw it as a little box with some, robot arms or something. They'll have an input, have a conveyor belt on the output or something, right? And, I think back to this time, they were working with more machinery than, what we have now. I mean, physical moving things, right? So I don't know how kind of language comes about and constructs these metaphors of which we think about these problems with.
One thing that's kind of interesting with function, you're actually onto something kind of interesting. So in the paper about lambda calculus, one of the things that he talks about is just what is a function exactly? And it's like, and he kind of talks about like a function is something like some input comes in and it produces some output. And he kind of leaves it just totally as that. Like that is the essence of there's like an argument and then you replace it and some output comes out. And one thing that he actually talks about is like keep in mind they're trying to prove like all of mathematics. And they're thinking about way more than numbers. Like in a math class, you often think of like, you have a function, you pass it 2, and then you get like 4 out of it. In one of the things in the paper is he talks about things actually from the actual calculus. Like, let's say you have a function and you want to compute the derivative of a function. Well, that's a function. That would be a higher order function where a function comes in and then it computes it figures out what the derivative function is, and the derivative comes out. So they're kind of thinking about like functions in this like really generic way where it's just like something comes in, something comes out, and it can describe everything. Just if you want to do numbers, that's fine. If you want to do functions, that's fine. But it's very kind of weirdly generic. And everybody got this data thing up here? I always find this kind of deeply sort of weird. Like the first time I saw this, I was like, no way, like what? Like building a data structure out of functions like that. One of the reasons why I'm having you do this, by the way, is how do you do subtraction? And how do you get the previous number? And what in the world could this possibly have to do with pairs or data structures? So one thing that I forget, I think you might have asked it, like how do you get from the one number to the previous number? Like you have the number 3, right? So here's your implementation of 3, f of x, like that. How would you get 2 out of that?
Maybe make your successor function always give you a pairing.
You're on the right track, actually. Now, maybe not the successor function, but one approach for this, and this is a total hack, by the way, is you could start with 0, 0 as a pair, and then you could ratchet your way up to to 3. Basically, you could essentially say, oh, I'm gonna like go up to 3. But as I go, I'm building pairs, where like you have the pair where it's like the first thing in the pair is the number, and the second thing in the pair is the previous number. Maybe I could use that to figure out how to get the predecessor number. I actually already kind of did an example of that. I had this weird tuple thing. I don't know whether you remember that. I'm not even sure it's in my environment here. Like I had this like weird tuple thing. Well, I'll type it in again. I had this function. Maybe I'll call it t here, where you. I had this weird thing where I was making a tuple where I did like this. And then I did some weird thing where it's like, take 3 applications of t and then apply it to the tuple 0, 0. What this thing is doing is like this t function, if you make a tuple, like there's your tuple, and then you apply it to A, it basically ratchets its way up through the numbers. Maybe I could do something like that. I mean, this is kind of, we're in the Python world right now, but maybe you could do something along that line.
And kind of metaphorically, this feels like, if you have a crank and it's always turning right, you just turn that crank upside down, and now you have a left-turning crank, right? We actually don't care that these things are zeros or ones. We just care that the arm is turning in a certain direction, and so it seems like it's easy to get hung up on the fact that there's 0, and 0 kind of means something to us as people, right? And that negative number somewhat means something. But in a very strictly mechanical sense, you're just performing these actions, right? It's a right turn or it's a left turn, and that's really all it is. So you just have to figure out how to inverse this certain
This isn't
situation.
even really reversing the direction. It's turning the crank on something that produces something a little bit different, basically. It's what we're going to do with this is like we could take that t function and turn it into let me do it with the lambda here. So we could do this in the lambda calculus. Like we could write this function t where it's like, okay, give me a pair, and then I'm going to do exactly what's up there. I'm going to basically say I'm going to do a cons. That's the act of making the tuple, right? So I'm going to do a cons. And the first element of the cons is basically the successor of the car, of the P. Try to say that a couple of times. So it's like the first item is basically take the, car is the leftmost one, the first one, yeah. I think that will work. So we could write like something like that. I mean, it's basically doing the same thing as the other function. It's just written in kind of using our terminology here. So like P0 is basically, that's the car. +1 is the successor of that. And then P0 is the car again. So you could write like a function like that. And it's like, okay, what is happening there? Well, if I were to take like one of my numbers, like 4, and apply it to t, and then apply it to like a starting point, like that, this is exactly the same thing that I was doing with the Python thing above. You get this result back. Let me save it here. And you're like, well, what is that? Well, it's basically a pair. So if I were to look at the first thing in the pair and then apply it to like my inker function or something, it comes back and says, well, that's 4. I mean, it's like it basically ratcheted its way up this like sequence of pairs. And then the second one is the previous number. Yeah, question here.
I anticipate this is the next thing you're going to say, but like that means we're only storing one previous. So like, sure, we can go back to this previous one that we've stored, but we still can't undo function calls. And so are you going to store all of them back to 0 all the time, right? Like, or you have to count from 0 every time?
Yeah, it's not stored. This is a horribly impractical way to do this. I mean, no, it's not stored. So like if you wanted to get the previous number to like 10,000 or something, we've got to do like 10,000 function calls to get up to 10,000. And then we go back one and throw it out. But no, this is how you do the predecessor though. Like the way the predecessor works is you basically take a number. Okay, so here's your number n. And you're going to apply that number to this like t function, which means you're going to ratchet your way up. You're going to go, 0, 0, 1, 0, 1. You're going to work your way up. And then when you're done with the whole thing, you just discard it and you take like the cutter of it. Whatever the second number is, that will give you that.
So it feels wildly impractical because my brain has already abstracted away the fact that a number is all of the calls from 0 up to that number anyway, right? Like that's why my brain was okay.
But it's like if I've done that right, this should work. Like we had this example I think where we did like 4 applied to 3. I don't know whether you remember that. And we got this crazy result where it's like, oh, that's 81. It was like doing exponentiation. If this predecessor thing is working, I should be able to say B is the predecessor of A. And the predecessor of A better be 80, unless I've done something wrong here, which it's possible that I have. Oh, I think T needs to have, you need to apply T to 0, 0. So let's, and apply to T, 0, 0. Okay, well, let's try it out here. So, $80. Okay, so it's this is like just like mind blowing. I mean, and again, it's like wildly impractical. Like you would never in a programming language, like if you wanted to get to the previous number, you're not going to count up to the number and then go back 1. I mean, why would you do that? And in some sense, you're sort of seeing, like this is the more mathematical side of this thing, where it's like if you're just talking about pure math, it all exists in this kind of world of like infinite abstraction, and you're not like this is not an implementation so much, but it's like a way of showing that you can get to the previous number if you need to. Yeah.
Is this kind of similar to async programming in that you define a behavior and then at the very bottom you shove an event loop into it and then let the magic work?
I have no idea.
Okay.
You think it needs an await in there somewhere? We should write a PEP for that and then run it over to the language summit, which is taking place down the hall there. Okay, so let's see. Do people have that entered? Do I need to leave the code up there for a second? I do think that's kind of an ingenious hack, actually. It's like, how do I get the previous number? It's like counting up with, like, basically making a bunch of pairs where you count up, and then you just store the number in the previous number, and then you toss the first number away. I mean, it's like, I'm not sure I would have thought of that. Like, if I had just given like a blank slate, you'd say, give me the previous number. I'm not that sure that would have come to mind, but.
So what is a pair? Is a pair like a state change? Like a state 1 is the left-hand side and state 2 is the right-hand side? Like, I mean,
So
I know that it's two things, but
it's like a pair. You have two values, and it's a function where you give it, like, you pass it a function to select one of the two values. Everything is a function. Yeah.
I don't know. Weird.
I'll leave that up for a second there. I forget who asked about equality, but that is actually kind of like a next step for this thing. Keep in mind, we're kind of building up some machinery here. So we do have the ability to go down now. We can you could implement subtraction, by the way. I should do subtraction. Subtraction turns out to be fairly easy. Like, if I want to take 5 and subtract 3, or subtract 2 from it, how do you do that? Well, you apply the predecessor function 2 times to 5, right? So if I wanted to subtract y from x, you would just do y applications of predecessor to x.
No, you said you always have to go upwards, right? You never start going down.
Let's just make sure that works there. Yeah, okay, so that works. Yeah, subtraction, it's like once you can get to the one number before, then the way that subtraction is it's like you just do that so many times. There'll be a quiz on this later on here. Now, the thing that I'm having you do next is actually, if you can test a number for 0, this allows you to start sort of checking things. Like why would you want to test a number for 0? Well, if you can start doing tests, then maybe you could start thinking about control flow. Like if statements, right? Like, how does an if statement work, right? It's like you have an if, and then you test something, and then you pick one of 2 branches. That would be a kind of an interesting feature to have. If we're going to do like programming, right? So the next challenge here is, how would you test a number to see whether it's 0 or not? Let me give you a hint on this. Numbers, keep in mind that a number, like if I have the number 2.
Is that different? Sorry.
It was basically that. And the number 0 was that. Numbers are always going to take like two inputs there. Do you have a question on that? Yeah. So keep in mind, numbers, they always have these 2 inputs. There's always an f, there's always an x. If n is a number, then it's a function that has these 2 inputs. It has an f and an x. How would I make that return true if n is 0? A little hint on it. So the behavior of 0 is that it always returns the x. Like if you have 0, It just universally returns the x. So I'm going to do that in my is0 check. Basically, if n is a number and it's 0, I'm just going to return true because it's like, that's what I'm trying to test, basically. If it's 0, it's true. So if n is 0, that is definitely going to return true. Still with me on that? Now the question is, what do you put here? Well, the thing that you're very close. The thing that's going to go here is you can make a function that just always returns false. Keep in mind the second argument or the first argument to a number has to be a function. So this is a function, takes an argument, but we just totally disregard the argument. We just always return false. It turns out that works. So if we do is 0, 0, it comes back as true. If we do is 0, 1, it comes back as false. Always comes back as false for the other number. Essentially what's happening with that is the 0 is kind of like a special case where the function is actually never called. Like this false function just never gets executed. Instead, you get true back. So if you have any other number, then this thing gets called, and it's like, well, that's just always false.
Just a realization of something that I found my brain doing that helped, that might help somebody else's. Sometimes you use f, and I'm used to thinking f as a function, and yes, in this case, it's going to be a function, but it's not the name of the function, it's actually the argument. So
It's
right there,
the argument, yeah.
the lambda f in the middle with the false is not, f is not the function, it's accepting an argument.
It could
So,
be anything. It could be
yeah, I put
x,
X
it could
there
be
because
g, it's...
F has special meaning in my brain, and I keep conflating it in weird ways, and anyway.
The fact that everything is a function here is just like mind-blowing. So I'll leave that up for a few minutes here. Oh, I don't know. Like if I said is 0 is 0? I'm not sure what that is going to do. Well, it comes back as true, but I'm not exactly sure what to make of it. As a Python programmer, I'll just say that's some kind of duck typing thing, and I'm not sure what that, yeah. It works, but you don't know why and what the answer is. So let's, technically not true. Maybe it's a type error of some kind. Okay, so where this is going, okay, so think about what we've kind of got. We've got Boolean logic, we've got add and subtract, we've got multiply, predecessor, we have the ability to do data, we have the cons thing. Essentially what you have built is a kind of a weird assembly code of functions. It's pure functions, but think of it as maybe like an instruction set or something, where it's like we have all these things you can do, and, or, not, suck, pred, add, mul, sub, cons, car. You know, you've got all of this stuff, and it's kind of like machine code in a way. I mean, it's a very strange kind of machine code in that it's so abstract. I mean, it's like just purely in this world of functions where it exists. But if you have that, maybe you can start doing more interesting things like writing recursive functions and other things. So maybe a challenge here, could you implement like a factorial function? I'll do it in kind of a normal Python way first, just could you implement that? I mean, this is a function that's like turning the crank. It's actually doing kind of interesting stuff. Can that be implemented using the the assembly language that we had on the previous thing? And so let's actually try that out. Here's how it's going to work. The argument to fact is n. That's going to be the argument to our function. We're going to take a number. What is the very first thing that you're doing in the function? You're doing an is0 check. So we're going to do a check is0 of n. What is that going to return, by the way? It's going to return true or false. And like, what do true and false do? They pick values out, right? So I'm gonna kind of break this across multiple lines, but true and false kind of act like an if statement. Like true, you have two values, right? A and B. You pick one of them. That's what's going to happen here. So like, what is the true part of this? 1, right? What is the false part of it? If it's not 0, well, then we're doing like a multiply, right? We have a multiply operator where we're going to multiply n by fac by the predecessor of n. Fair number of parentheses there. Make sure it's not a syntax error. It's kind of admittedly it's a little tough to kind of wrap one's brain around that, but it's almost a literal translation of the Python code into this kind of low level machine code. Is n 0? If it is, we're going to return 1. If it's not, we're going to multiply n by factorial of n minus 1, or the predecessor of n. Did anybody get that to work? Yeah. Yeah. It's kind of like the I don't know, like one of these like battle scenes, where like the evil villain dies and the whole evil army dies at the same time. It's like we've kind of worked up to this point, and now the whole thing just blows up in infinite recursion, and we're like, it's like totally disappointing and so forth. So if you do that, do people get the maximum recursion thing? What's going on with that?
Well, the fact that we have maximum recursion def means we've inadvertently invented a loop. I think.
We have definitely invented a loop, but it has run away from us.
Is it actually wrong, or is Python just complaining because we're misusing Python? Right? Like what if we were able to increase our maximum recursion depth?
No.
Okay.
Like increasing the recursion depth will not help this. The basic problem here is that we are using a highly inferior programming language called Python. I say that facetiously. Here is the gist of why this is blowing up. If let's say I have a function f of x, and I return like 3 times x plus 1. If I say f of like 2 plus 10, how does that work exactly? It does the argument first, and then it calls the function. Like basically Python evaluates arguments first. Like so if like the arg goes first. And essentially what we have done in Python is we have written a function that is kind of like an if statement. I mean, for lack of a better description, we've written a function like choose AB, where we have a test. Like we have something that looks like this. Like if T, return A, else return B. That is kind of what's going on with like the true and false, basically, or the is zero test in a sense. We're basically saying like imagine like let's say you had like a is 2 and b is 3. We've written a function where it's like, okay, choose, like if a less than b, choose a, otherwise b. We've written like a conditional, essentially. And the problem with that is that you can't do that. Like here's an example of how you can't do that. Like let's say I decided to choose a not equal to 0, a 1 divided by a. Like that's right. So let's say you've wrote a function like that. It's basically gonna blow up because it's actually trying to do both of the arguments at the same time, right? I mean, like in that function, it's basically saying, oh, I'm doing the a, and I'm doing the 1 divided by a at the same time. And like it just like explodes. Essentially, it doesn't know what to do. That is not how control flow works in most languages. Like if I were to write this out using like an if statement in Python, like a if a not equal to 0, else 1 divided by a. Oh, maybe it should be equal to 0. Let's try that. That does not blow up. Whereas my other one does. The reason that this one doesn't blow up is that Python is smart enough to not go down the else. Like it basically does the check first, and then it decides, like, I'm going to do one or the other. And that is what is killing our code up here, is that when you do these functions like the 1 and the multiply, it's basically doing both. Like it goes down both paths, and it turns out that the second path just explodes in infinite recursion. Essentially, it has to do with Python like eagerly evaluating arguments. It's like it always wants to evaluate arguments, so it's like running away with the calculation.
Is it possible to turn that off?
Yes, but not in the way that you might think. No, the solution to this is actually, yeah, you can turn that off, but the question is, how do you do that? Let me go to the interactive example here. So let's say you wanted to turn off 1 divided by a. This is the thing that has the 0 division. So let's say you wanted to get rid of that. How would you not do that? Well, one of the ways that you would not do it is you could shove it into like a 0 argument function. Like you could just say f is lambda, like no arguments. And then you put the 1 divided by a in there. You're like, what did that do exactly? Well, what you're doing there is you're basically delaying the calculation to some later point in time. Like if I want to do that, then I could put parentheses on it, and I could let the thing fire, basically. And it turns out that you could do that with like this choose function. I mean, like you could say choose t, a, b, if t, return a paren. Keep in mind, this is a really subtle change here. Like you're evaluating only if the thing is needed, essentially. So what you would do with that is you could say choose a equals 0, and then you would shove like basically lambdas into this thing. Oh, I need to have like my thing there. That is admittedly a little weird. It's basically addressing like a problem with Python. I mean, Python wants to like eagerly do all the arguments. What we're doing with this lambda trick is we're basically pulling it back from the brink, essentially saying like, okay, no, do not, the arguments basically are functions, and I'm only going to evaluate that function if I need to go down that branch. That is essentially what's happening. So there's a question in the back there. Everything is more sane doing it the way Python does it. I think most programmers, like when you call a function, you like to have the arguments evaluated. So almost every programming language works in the way that Python does. So.
Yeah, if it didn't do it, it's not even obvious what would happen. Like it would have to encapsulate the argument in some kind of a callable, which would only get executed if you like if the local scope reads that argument. It would be.
Yeah, if all the evaluation gets delayed, then everything just gets crazy. I mean, it's like it just being a. Yeah. Yeah. No, you would not do this. Like I mean, this is sort of illustrating. I mean, you're kind of getting into like this evaluation issue with Python. Like, how do things happen? And it turns out that it blows up the what we've done with the Lambda calculus, because it's like this factorial thing is not working because it's basically evaluating like both branches kind of at the same time, and then it's like exploding. Now we can fix it. Now, I will just preface this as saying that this is mainly required because of Python. You know, basically the eager evaluation. One way that I can fix this is I can essentially implement like a different implementation of true and false. I apologize for doing this, but the way that you can redo it is you're going to introduce a function call. Like that. And then I'm also going to have to redo the isZero function. So I'm going to have to, I'm basically going to have to introduce like this like extra function call in there. And then in this fact thing, I'm going to have to do this like Lambda trick. I'm not super happy about doing this. This is really not part of the Lambda calculus that we're doing here. This is purely a hack to get Python to not do both branches of that, of the if, basically. So I can make it work, but I've got to do this like patch up. I'll give you a few moments to kind of type that in. So if you do that, it's gonna work, and it's actually this concept of like when things evaluate is actually a really big deal in functional programming. I mean, if you get into some of these other languages like Haskell and all sorts of stuff, they focus a lot on this. Like, when do things evaluate? Is it evaluated lazily? Does it evaluate eagerly, and like when do things happen? And we're kind of facing that. We're sort of facing that here. Again, having to work around some limitations of Python, and that it does not allow this kind of lazy evaluation. I don't know. Do you have a question, Yarko? Are you doing a swag bag, like promotion?
You have to show up tomorrow. Here.
No, okay.
Make sure you don't
Yeah, okay. Yeah, it's at the end of this tutorial, it's like Thelma and Louise or something. I'm running away, and then all that. Did anyone get that to work? It's pretty mind blowing. It's like wow. Okay.
Can I ask a question?
Recursion here. So, yeah.
So I think at the beginning you said like everything needs to be one argument. Or do you just get around that by having a dummy like argument basically?
Well, we have to break that rule.
I've had to. Yeah. I've had to break it here, and actually you could put a dummy argument in there. But I'm not sure that it adds clarity, actually. No, I was actually thinking about this in the preparation of this tutorial, because it's like, if you add a dummy argument, then I have to put something in here. Like I could just pass like some
but doesn't that still break
dumb.
the rule in spirit? I mean,
It breaks it in spirit. No, you could make it work by just passing a dummy argument. I kind of felt, honestly, in prepping it, I sort of felt like this is already a hack to kind of deal with Python. And I thought just leaving it as just zero argument, just acknowledge that, okay, this is a Python-specific hack that we have to do. It's a little unfortunate. I mean, it's like normally in the Lambda calculus, you would not need to do this because it's not, like the Lambda calculus doesn't specify like an evaluation order. So like mathematically, it's not needed, but it's like a purely Python required thing here.
I would just argue that it's not a Python requirement, it's a programming requirement, right? Like, because like
Sure.
you said, most programming languages would do this, right? It's not, like Python does have a few things that it does that makes it weird compared to other languages. This is not one of them. This is a
No,
normal-
like you would have to do this in C, or you'd have to do this in Scheme or Lisp.
Right.
I mean,
In
Lisp
math,
kind of,
it works, but not
it's like
in- yeah.
The only place you probably would not have to, well, not the only place, but like you wouldn't have to do this in Haskell, for instance, because they do lazy evaluation and that. Now there is something kind of coming up. If you got that to work, we're not done with this yet. One thing that we are abusing is the fact that the Lambda calculus does not actually allow global variables. Like there are no global variables. There's no assignment. It's only functions. And all of this stuff that I'm doing, like with the assignment of the names, like fact equal is 0 equal and so forth, that is technically not allowed. Like you're not allowed to just make a variable and store it. Because this kind of implies storage, right? It's like if I make a name, it's like, oh, it must be storing it someplace. I can't do that. Like that is not a legal kind of thing to do. And it actually presents a really interesting programming problem when you start talking about recursion. And here's why it becomes interesting with recursion. If you're doing this recursive stuff, you have to refer to yourself, basically. Like that's the whole way that recursion works, right? It's like you have factorial, and it's like I have factorial, and then a bunch of stuff, and then in the middle of factorial, I have this like self-reference, right? Like, right, but how do I get myself? No, it's a weird problem. Like I want to do this in Python for a second, but like you have this function, like let's say you had a factorial function in Python. We're going to do it with Lambda here, just like, Lambda n, and I'm going to do it in kind of the shorter way, like 1 if n equals 0, else n times fact n minus 1. Okay, so let's say you had something like that, and let's just make sure that it works. Lambda. Okay, fact 4, 24. Here's here's the challenge. How would you rewrite that to not have a self-reference to yourself? Like to not have that fact? Like, how would you get rid of that? What? No, we're working purely with functions, so we can't do like for loops or anything like that.
You have to use a Y Combinator?
Eventually.
Okay.
Yeah, we're gonna. You're jumping the gun on where we're heading here, so we're heading to something like that. No, it's you can't have like basically you cannot have that global reference. Like this is like that is the thing that isn't like we do not want that. Okay, so that's like no, we're not allowed to have that. And so if you can't have that, there's this question of like, well, what do you do there? And one of the things that you could do there is you could pass it as an argument. At first glance, that's going to look crazy. Let me just shorten it up a little bit. I mean, you could do that. You could like introduce like an extra argument there and then just pass the function in as an extra argument. I actually already kind of did a horrible trick with that. Like I think at one point I said like if you had x is 2, you could actually say x is equal to like lambda y, and then apply it to 2 as this like totally just dumb thing that you could do in code. That is kind of what we're doing here, where it's just like, okay, if I can't have the fact in there, I'll just pull it out as an argument.
Wait, but isn't that a name error? You can do that?
No, this doesn't work in Python. Like, no. That's like, okay, so you're going to look at that and you're going to say, wait a minute. You're just like, no. Like all that happened there is you moved the fact out into this outer part, and it's like you're like Beazley. It's like, oh, come on, man, you can't do that. Like, what are you doing? So that you can't do that. Like you cannot have the fact there. Yeah.
But it seems like the factorial is just a name to help us describe that particular combination of functions. There's no actual storing of global things. We've just given it a name as a convenience for us to refer to that particular combination.
Yeah.
So anything that has that combination will then be a factorial. And if you
Sure.
change that combination, then it's just something else, and it's just some other name.
Uh-huh.
So why do we even care about storing that name?
Yeah, we don't need the name. But
So why do we care about globals or variables? It just doesn't even matter.
Well, because you need to represent the
I need to yeah, I have to. The problem here is I need to have a reference to myself.
I mean,
like
as an
in order for
implementation,
factorial
yeah,
to
but
work.
on the math level, who cares?
Yeah. Yeah.
Uh,
Well,
that's not Python.
even kind of on the math reference, it's like if you're going to express recursion, there's kind of this like, okay, you're going to recurse, but like, how do you reference the like? There's kind of a weird cycle set up where it's like you're recursing, but like, how do you get a reference to the thing that you're recursing on? And no, it's wild. Now the solution to this will blow your mind, actually. Okay, so keep in mind I cannot use fact there. Fact, that is no. Okay, so that is gone there. So the solution to this problem is to do the opposite of everything that you've been taught about proper software, and to do the opposite of don't repeat yourself. And what is the opposite of don't repeat yourself? Repeat yourself. If you need to pass yourself in as an argument, you just cut and paste the code and do it twice.
I mean, you have to keep continually cutting and pasting until you get to your zero representation, right?
No, because
No, it's
F, right?
it's F. So this thing, the first argument is F, which is the recursive function. So I'm going to pass myself. I'm going to take the code and I'm going to paste it in there and I'm going to pass it in there.
That is one of the most ridiculous things.
Now it doesn't work. Now it still doesn't work. Keep in mind, this is not. If I try that, it's gonna blow up with some exception, and and it's like, okay, what is wrong? What is wrong there?
Well, because the very first time you're doing it, it expects a function. That's the thing. You're passing in an int, and which is fine for every.
No, he has to pass in the for function.
Yeah. No, the thing that's wrong here is I'm not following the API. Not to get back to APIs, but like the API to this thing is you pass a function first and a number second. And I'm not doing that. I'm not doing that here. Like when I do the recursive call and I say f of n minus 1, I'm not following the API. I'm just passing the number. I need the f. Like where's the f? I'm missing an argument basically. I have a 2 argument function fact like this, like the f and the n. That's 2 arguments. I'm only passing one of the arguments. So now there's this problem, like where do I get the second argument? You just pass it in. I think that's what you said. You just pass f. Like f is the function.
So just repeat it the third time, essentially.
So you pass it, like f is a 2 argument function. It takes an f and an n. The first argument is f. And so you just pass it as the second argument, or as the first argument. Works perfectly. Looks a little bad, a lot bad, like having the duplicated function function thing there. Yeah, we're going to get to that. Yeah, we're going to get to that. I guess we should do the slide update there. No, this is crazy. It's like, okay, so you can do a recursive function and just you don't need the name there. Maybe just to illustrate that the name is kind of unimportant, I could actually I could just take this code and just drop it. Let me come down here. Just drop it in like a print statement. Yeah, print function. Yeah. So you could just like print like lambda lambda, and then drop like 5 on it, like that, and it'll work. It's just like a big expression. I mean, if you really wanted to make this like hardcore, you could just put it inside an F string probably, and then it would work. I'm not going to do that, but that's it's kind of amazing. All right, everybody get that? Get that? Yeah, there'll be a quiz later. Yeah, question there.
That's depending on the short circuiting of the arguments, right? So if the first branch evaluates to 0, then it just returns 0. Or sorry, if the first branch evaluates to 1. Okay, cool.
Yeah, definitely the short circuiting. We need that, like that not going down both paths, and Python is kind of giving us that. So I want to say a little bit more about that. This whole thing, the whole repeating yourself part of it, should have made you feel like really kind of awful in a way. Like normally in programming, you don't want to do that. Like having to repeat, like cut and paste code. I mean, actually reading that is kind of making my eyes bleed a little bit. Trying to figure that out, and I want to talk about an alternate way of doing this. And before I do that, I want to talk about school for a second. So, I mean, I don't see anybody like head down on the desk really here too bad, but like in school, like in math class, did you ever have like that experience of like, this is so boring, I just want to die, and can the next 45 minutes pass? And then in trying to pass the time, there was like a common thing that like I used to do, which was to pull out my hand calculator, and then you just start like pressing buttons on the calculator, and you're like, I'm so bored. Like has anybody done this, like the square root thing, where it's like you get the calculator and you punch a number and you just start doing like square root over and over and over again, and like the numbers get smaller, and then eventually it hits 1, and then it just starts hitting like 1 and 1 and 1 and 1 and 1 over again. I can't be the only one who's done that, so I'm sure that everyone has done that. So one of the things that you were doing there is actually exploring one of the most interesting things of all about lambda calculus and recursive functions and other things. So one of the things that you found in doing that is you found something known as a fixed point. Kind of a mathematical term, but a fixed point, it's basically a function where if you give it like an input, you just get the input back. Like square root of 1 is 1. Turns out that 1 is a fixed point of square root, meaning that like if you just call square root like over and over and over and over again, you just end up back where you started. Okay, so you end up with something like that. That's an example of a fixed point. Basically, you have a function, you give it an input, you get the same thing back. And one question you can ask is like, is this in any way possibly related to recursion? I mean, what you're doing with recursion is you're kind of turning the crank on this function, like f of f of f of f of f. It's kind of the same thing that you were doing with the calculator, right? I mean, it's like, okay, I'm pushing the square root button over and over and over again. Is there anything that you can get from that? And so to talk about that, I'm going to go back to this factorial function for a second. So I'm going to do it as kind of the lambda version of it. Okay, so this is what we started with. Okay, this is our kind of our original function. And one of the things that we did in the previous part is we did this trick with the variable name. So we did this fact where we passed it in like an f. And then we did that. This was the thing there where it's like, well, that makes no sense at all. Like, I mean, like, what do you mean? Like, you have the fact on both sides of the equation there. I'm going to take out the middle part of that and put it into its own variable. I'm essentially taking out the part in the parentheses. So I'm taking that and putting it in its own variable. Maybe I'll put parentheses around it just to emphasize that. So if you do that, you're going to end up with kind of this weird statement at the end. I'm going to put some comments on this, by the way, because I'm not sure that the things that follow are not going to work as Python code for a second. So, but what's happening is I kind of took the middle of this thing out, and then you end up with this relation: fact equals r of fact. People kind of see how that came about there. It's like it's basically the sneaky variable trick where I've turned fact into a variable, and then kind of factored it out there. If you look at that last statement and you ponder it a little bit, it turns out that you'll realize that fact must be a fixed point of R. The whole idea on a fixed point is that you have a function where you pass it, you pass something in, and then you get the identical thing back. This is exactly the thing that we did with the square root, right? Square root of 1 is 1. This is saying that. It's basically fact, like R of fact gets you back to fact. So this R, that has to be a fixed point of whatever that, fact has to be a fixed point of whatever that R function is. Head should be exploding a little bit here. It's like, okay. I'm thinking of it just purely mathematically right now. Okay, so question over there.
So that then implies basically that fact is a fixed behavior of R?
I wouldn't say it's a fixed behavior necessarily, but it's the behavior of R is that if you give it this fact function, you're going to get back the original fact function, whatever it is.
So it is, one is a fixed point a kind of identity. Like you give something, you get the same thing back. And also when you use the term fact must be a fixed point of R, like R is also a function, right? So does that mean that there's other fixed points of it, or does it have just one fixed point? Or there must be some like set of R's that give you back things.
I think there might be a result, like there may be infinite fixed points of R.
And is there,
And it's
there's multiple
there's multiple
relations,
fixed
or
points. Yeah. See, one thing that's a little weird about this is we still do not know what fact is. Like this statement, like if I were to write in Python, fact equals r fact, that's not going to work, right? I mean, it's like, how is that supposed to work? Like, it's like fact doesn't even exist yet. So that's like invalid Python code. And we don't even know what we don't even know what fact is as like code. Like if I were to look at this, it's like I don't really know what fact is. I know what R is. R is this thing up here. I don't know what fact is. The only thing I know about fact is that if I can figure out what it is, then fact equals R fact. So I don't know what it is. I just know that if it's a fixed point of R, then that must be true. Yeah.
So can we really, because fact is just a name, are we really like asserting that that's like an equality and not just an assignment? I think that's kind of the thing I'm struggling with, is like 1 and square root of 1 kind of makes sense because 1 isn't like a name of a thing, like it's an actual value.
It's not really an assignment. No, you're yeah.
1 is the name of that particular 0 function incremented. 1 itself is a function.
Right, but like fact here, are we just saying here are we saying we get back the same function after we pass it into R?
Uh-huh. What this is, you're onto something. This is not really an assignment, but it's a mathematical relationship that is being expressed here. It's like, so mathematically, it's like fact is equal to R fact. Now, the big leap that we're going to take, okay, kind of getting near the end here. So this is the huge leap. And you're going to have to bear with me for a second on this. So, suppose that there actually was a function I have not told you what this is, by the way, but this is a typical math trick, right? It's like, well, suppose that there actually existed something that could compute what the fixed point was. So let's say there was some function y that existed in the world somewhere where y of r basically computed like the fixed point of r. Whatever it is, and we don't know what it is, but like let's just assume that there's some function that was out there that could do that. If that thing existed, and again, this is like very much math talk. Like, well, assume that it existed, and we don't know what it is, but assume that it's out there. If that thing existed, then you could say this. You could say y of r is equal to y of r. All I'm doing there is replacing fact. Like if fact is a fixed point of r, then I should be able, y of r equals r y of r. So you could do that. It's still not clear how in the world that would help you now, because it's like, okay, great, like what? Okay, awesome. You have like the y of r is equal to ry of r. I'm going to do my little recursion trick. Basically, what you have there is you have recursion. And what was the recursion trick? Well, the recursion trick was this thing where you pulled it out into a variable, like that. That's what we did with the fact function, right? It's like we basically said, oh, we're going to pull fact out of there, and then we're going to put it as an argument. But one of the things in the trick is we basically said you couldn't do, like that doesn't, like you can't just put the YR in there. What you have to do is the thing that you didn't want to do, which is the repeat yourself trick, right? Like when we did the fact, it's like the solution to the fact was to repeat yourself. So it turns out that we're going to repeat ourselves. Yeah, lowercase x there. Okay, so this little trick here, this is the repeat yourself trick, okay? When we did that trick with the fact function though, there was one other thing that we had to do. Do you remember that? Like we had to do the hack with the f. Do you remember that? Where it was like if you looked at the fact thing, we had to do this like f of f thing. So if we're going to do the repeat yourself trick, we have to do that here. Instead of having x, I have to say x of x. I have to do the trick on it. Maybe I'll do that as a separate step. Okay, so that was that kind of necessary hack, like the extra x in there, so the extra call. And if you look at that, it's like, it's almost starting to look like a formula, actually. One thing that we could do with it is pull out the r. I probably have too many parentheses there. So you got the R there. It looks like you have R on both sides, actually. So maybe you could just drop it. Okay, so maybe you can end up with something like that. This thing that we're deriving here, this is this thing known as the Y combinator. So as far as I can tell, it's an invention of Haskell-Curry. It is a device basically to do recursion in like functional languages without having like self-references. It's a little like hairy to like derive that, but it's basically based in this like kind of fixed point idea, and the way that you use it is you would write out kind of like your recursive relationship here. Like you would say R is that, and then what you would do is you would just say fact is equal to Y of R. And if that thing is working, it should basically produce like a recursive function for you through like serious magic. In theory, yeah. One of the reasons for doing this is like that term Y combinator is something that's, you know, often you hear about that in kind of hacker culture and stuff, and it's like, it's kind of interesting to see what it is actually. I mean, it's actually a device for kind of doing recursion. If you do it, you're going to find that it does not work. In typical Python style, question in the middle there.
I'm just wondering what the expanded version of the dot in the Y.
Oh, it's colon basically.
Okay.
Yeah, it's colon.
Thank you.
We're getting near the end. We're almost done here. If you type that up, you are going to find that it does not work because of an infinite recursion error. And without getting, well, okay, so that is actually getting back to Python's evaluation problem, like the fact that it does eager kind of argument evaluation. And the solution to that problem is, ironically, the solution to all Python problems, which is, you're on the right track. No, I wasn't thinking meta classes because we don't have classes here. If you want to solve any problem in Python, what do? You put a decorator on it, right? I mean, like, no, like, so let's say you have a function like 2 times x plus 1. If I were to write a function g of x where I just flipped it around and said f of x, okay, I got the, well, okay, got an error. I'll forget about it. Okay, so if I were to do that, that's basically what you're doing with a decorator, right? It's like you're writing a function that wraps around another function, but it produces basically the same kind of result. For reasons that I will not completely explain.
For G to take F or X as an argument?
No, it takes X. G takes X, and then G just takes the X and passes it along.
Normally you put the def F inside of the G if you were writing a normal decorator.
Yeah, if you're writing normal, yeah. This is kind of like a decorator kind of expanded out. It's wrapping, basically. You write a wrapper function. It turns out that if you do that, you can do this in kind of the lambda calculus. It's going to look a little weird, but what I'm going to do is I'm going to take an F, and then I'm just going to introduce like an extra argument, and then I'm just going to pass it through. I have a feeling I'm probably missing a parenthesis in there somewhere, but let's try that. Okay, so that the infinite recursion is gone at this point. Seems to be working there. There will definitely be a quiz about that one. It's part of what's happening there. It's deferring evaluation so that it doesn't get this like infinite recursion. Turns out that lets you write these like recursive functions. As you stare in that in sort of disbelief, perhaps. I mean, we can do like we could do Fibonacci number. This is kind of a recursive, like Fibonacci thing. So you could like say fib is equal to r, like y r1, for instance. I don't know what the 10th Fibonacci number is, but it's... Yeah, head's fully exploded here. Yeah, if you've heard of the Y Combinator, that's what it is. Something for enabling recursion. Question in the front here.
So I'm trying to think like what is the relationship of all of this and this kind of function substitution to the idea of currying, right? Which is obviously named after Haskell B. Curry of the language, right, and all that. Which I mean, informally, I always use kind of currying as freezing a particular parameter of a multiple parameter function until you either get to if you had 4, now you have 3. If you have 3, you have 2. And eventually you either get to 1, which is kind of how we started with these one function parameter functions. Or, maybe you just get to 0, which then becomes just the callable itself.
Yeah. The question about currying, I mean, currying in some sense is this conversion of multiple arguments to single argument.
I mean,
so that's, yeah. Yeah. Yeah, I don't think recursion is necessarily related to the currying thing. I mean, the currying is more of just all functions take one argument. And then, instead of having multiple argument functions, you can have the one argument function. It's actually kind of interesting that you would bring up currying, by the way. We're basically at the end, but I'm going to make a few comments. This business with combinators is actually the work of another guy. There's this Moses Ilyich Schoenfinkel, who's kind of known as the inventor of combinatory logic. And it turns out that all the Lambda calculus papers reference this reference this guy. Curry built on his work. It turns out that this guy is the one who invented currying, actually, in the 20s. Like, so he's actually much earlier, and it's like cited in the papers. It's sort of a sort of interesting story on this. It turns out that you can actually get rid of the requirement of defining new functions and derive all of lambda calculus from a few so-called like combinator primitives. I'm not going to get into that here because I don't fully understand it yet. You know, it's like my head's already quite exploded on the previous stuff, but this is kind of an earlier thing. This guy's kind of interesting, actually. His story is sort of tragic. You know, I think he went insane at the age of 28, and then all of his math papers got burned for fuel, like in the Russian winter in like 1942 or something. So like not a lot of information is known. I mean, he has some papers, and you know, he is cited by kind of Alonzo Church and some of the papers on lambda calculus, but sort of interesting. So some final comments on this. Okay, so we're basically at the end. And I was trying to think like what to even make of this tutorial. I mean, I think like having seen this the first time, I was just like, this is just insane, and like why would you do this? And, you know, like in the description of the tutorial, I was like, you're not going to do anything practical in here. Like I don't see you walking away just saying like, oh, I'm going to implement my web app using lambda calculus or something. So like no. Like, I mean, you're not going to make a programming language that literally operates in this way that we've described. But I think there is something kind of interesting about it. I mean, you know, one thing I think is interesting is I think a lot of the mainstream programming languages are kind of based on this abstraction on hardware. Like if you think about Python or C or Java or something like that, like so much of it is like, well, you have like operations, you have memory, and you have pointers, and there's this idea of the hardware running machine code, and there's a whole bunch of stuff that's going on under the covers. And I think as a programmer, it's kind of useful to have that as a mental working model. Like, oh, there's memory, and there's arrays in memory, and there's this stuff going on. I mean, even though that's your model, you're not writing machine code usually. I don't know, is anybody writing machine code in here? Like assembly code? I mean, we're at a Python conference. I'm not writing machine code. But I'm probably thinking about the machine though. You know, like if I'm doing NumPy or something, I'm thinking about memory and arrays and all this stuff. I think there's maybe something similar going on with kind of the lambda calculus. Like if you're going to start exploring sort of functional programming languages, like you get into like Haskell and Scala and Scheme and Lisp, and you start branching off into other topics like type theory and other things, you actually find that a lot of this lambda calculus stuff is all over the place. One of the books that I'm kind of working on right now is there's like a types and programming languages book talking about type theory, because I don't actually know that much about type theory, and I'm trying to wrap my brain around it. The very first example in that book is lambda calculus. They're like, oh, let's just have this hypothetical minimal programming language that happens to be called lambda calculus, and we'll put like types on it or something. So you start to see it like everywhere. And even though you would never maybe like code with the lambda calculus, it's more of like maybe a mental model of functional programming, like doing things with functions and different ways of composing functions and other things. So I think that would probably be like maybe the takeaway from this is just kind of an exposure to this like really amazing kind of functional programming world and some of the stuff that you can do there. And I think that's it. Yeah, the end of that. So yeah, thanks for coming to this. Just as a little background, if you're interested in kind of getting more into this kind of stuff, the avenue for me getting into it is I started doing some study of this structure and interpretation of computer programs book, or the famous the SICP book. It does not cover lambda calculus. Like that's not part of that book, but it talks a lot about functional programming and some of these things. That is actually what kind of got me interested in that. And so, you know, if you're looking for kind of maybe a gateway to kind of learning more about this kind of thinking and all that stuff, I would look at that. You know, it's kind of a starting point. So that's it. That's all I've got. We can take a few minutes of more questions. Otherwise, I got to let you go to lunch here. So. All right. Thanks for coming. So.